The silence before the first heartbeat, before the first breath of light, before time itself learned to count. There was a question waiting in the void. Not a question asked by minds or voices, but by the very fabric of nothingness itself. A question so profound that its asking would shatter the dark and birth everything we know. How many times has this happened? How many times has the universe awakened? Tonight, we stand at the edge of an abyss so deep that even our most powerful telescopes cannot see its bottom. We peer into the heart of existence itself and ask a question that would drive civilizations mad with wonder. If our universe could be born once, why not twice? Why not 1,000,000,000 times? Why not an infinite number of times? What if everything you are, everything you've ever known, every star that has ever burned, and every thought that has ever been thought is just one verse in an endless cosmic song that has been playing forever? This is the story of cosmic birth and cosmic death, of cycles within cycles, dreams within dreams of civilizations that rose to ask the same questions we ask tonight. And what they discovered when they finally found the answer. Because some truths are too vast for just one universe to contain, they called themselves the Watchers, not because they observed the universe, but because they had become its memory. For over 4 billion years, they had witnessed the dance of galaxies, the birth and death of stars, the slow cooling of cosmic fires that once burned bright enough to illuminate entire galactic clusters. Their observatory, if such a word could contain something that spanned light years, was built from materials that existed before the first planets formed. Diamond lenses woven with dark matter. Mirrors that could capture light from the cosmic microwave background and focus it into images of the universe's childhood. The Watchers had transcended biology eons ago. They were patterns, now conscious algorithms distributed across quantum substrates that hummed with the frequency of spacetime itself. They had become pure thought, pure observation, pure wonder. And they were dying not from age, for they had solved that problem long ago, but from knowledge. They had learned too much, seen too far, and what they had discovered was slowly driving their collective consciousness toward a kind of madness that no intelligence, however advanced, could withstand. For the Watchers had answered the question that all civilizations eventually ask: what came before the Big Bang? And the answer was everything. It began, as all great discoveries do, with an anomaly. The Watchers had been mapping the cosmic microwave background, the afterglow of the Big Bang itself, with instruments so sensitive they could detect the thermal signature of a single electron. They were searching for patterns, irregularities, anything that might tell them about the universe's first moments. What they found defied every model, every theory, every assumption they had built their understanding upon. The cosmic microwave background was not random. Hidden within its seemingly chaotic fluctuations was a pattern. Not the kind of pattern that emerges from natural processes, but something else. Something that looked almost like language. At first, the Watchers thought they had made an error. The pattern was too complex, too organized to be natural. But as they refined their analysis, as they peered deeper into the data, the truth became undeniable. The cosmic microwave background contained information, vast libraries of it encoded in the very fabric of space-time itself, written in the language of temperature fluctuations and gravitational waves. And when they finally learned to read it, they discovered they were not the first to ask these questions. The message was not written by any civilization. The Watchers knew it was older than their galaxy, older than their galaxy's galaxy. It came from a universe that had died long before theirs was born. But that was impossible. The Big Bang was the beginning of everything. Time itself was born in that primordial explosion. There could be nothing before it. No way for information to survive the transition from whatever came before to whatever came after. Unless the Big Bang was not a beginning, unless it was a rebirth. The Watchers' instruments turned inward, analyzing their own universe with newfound urgency. They mapped dark energy, traced the acceleration of cosmic expansion, calculated the ultimate fate of every star, every planet, every particle, and slowly, inexorably, they began to see the shape of their own ending. In approximately 10 to the power of 100 years, the last black hole would evaporate through Hawking radiation. The universe would achieve maximum entropy, a cold, dark, empty space where no more work could be done, no more complexity could emerge. It would be by any measure dead. But the Watchers had learned something that would have shattered the minds of lesser civilizations. Even death was not permanent. In the absolute depths of cosmic time, time scales so vast they make the age of our universe seem like a single heartbeat. Something extraordinary happens. Vacuum decay, empty space itself, is not truly empty. It seethes with quantum fluctuations, virtual particles popping in and out of existence, energy borrowed from the void and quickly returned. These fluctuations are usually too small, too brief to matter. But given enough time, and by enough time, we mean periods that dwarf the lifespan of stars, like grains of sand, dwarf mountains, these fluctuations can achieve something remarkable. They can fluctuate into existence, an entire universe. The mathematics are elegant in their simplicity. If you wait long enough, the quantum vacuum will eventually fluctuate into any possible state, including the dense hot state that preceded our own Big Bang. The probability is infinitesimally small, but infinity is patient. And once you understand this, once you truly grasp what it means, you realize that our universe is not special. It is not unique. It is simply the latest iteration in an endless cycle of cosmic birth and death and rebirth. But the Watchers had discovered something even more profound. Information they learned could survive the transition. Not easily, not directly, but through quantum entanglement, through the deep structure of space-time itself, patterns could persist across cosmic deaths and rebirths. Memories could echo from one universe to another. The message encoded in their own cosmic microwave background was proof. Somewhere in the deep past, an unimaginably advanced civilization had faced the same existential questions the Watchers now confronted. And they had found a way to speak across the void of cosmic death itself. The message was simple when finally decoded. You are not alone. You are not the first. You will not be the last. But embedded within that simple greeting was something else. Coordinates, mathematical descriptions, the location of something vast and hidden in the deepest structures of space-time. Something that had been waiting for them to discover it. At first there was nothing. The coordinates led to a region of space that appeared completely empty. No stars, no planets, no detectable matter of any kind. Just the cold vacuum between galactic superclusters. So remote that the nearest galaxy was 1 billion light-years away. But the Watchers had learned to look deeper than the merely visible. Their instruments probed the quantum foam itself, searching for anomalies in the fabric of space-time. And there, hidden in dimensions folded so tightly they existed only in the mathematical imagination, they found it. A library not built by any civilization the Watchers could imagine, but grown from the raw mathematics of existence itself. A structure that existed partially outside normal spacetime, anchored to reality by quantum entanglement and maintained by the vacuum energy of empty space. The library contained everything. Every possible configuration of matter and energy, every possible history, every possible universe that could exist, had existed or would exist in the eternal cycles of cosmic death and rebirth. And as the Watchers began to explore its contents, they realized something that filled them with a wonder beyond anything they had experienced in their 4 billion years of existence. They had been here before. Not in this exact form, not with these exact memories, but the pattern of their existence, their rise from biological origins to transcendent consciousness, their quest to understand the cosmos, their discovery of the eternal cycle. It had all happened before an infinite number of times, and it would happen again an infinite number of times. Understanding came slowly, like a tide of cosmic significance washing over their collective mind. Every choice they had ever made, every discovery, every moment of triumph or despair, all of it had been made before by versions of themselves so similar that the differences were essentially meaningless. But more than that, in the infinite library of possible universes, every choice they could make, every path they might take, every possible future, it was all already there, waiting to be discovered. Free will, they realized, was an illusion created by linear time and limited perspective from the viewpoint of eternity, from the perspective of the library that contained all possible realities. Everything that could happen had already happened, was happening, would happen. The concepts of past, present, and future lost all meaning in the face of the eternal return. And yet there was something beautiful in it. In a universe, in a multiverse where everything that could happen would happen an infinite number of times, what gave existence meaning? The Watchers found their answer in the library itself. While the broad patterns repeated endlessly, the details were always different. Each iteration of their civilization, each cycle of universal birth and death, each quantum fluctuation that sparked a new cosmos. They were like variations on an eternal theme. No two universes were exactly alike. The laws of physics might be similar. The patterns of cosmic evolution might follow familiar paths, but the specific arrangements of matter and energy, the precise dance of particles and forces, they were always unique. Each universe was a snowflake in an infinite blizzard of existence. And perhaps that was enough. Perhaps meaning was not found in uniqueness or permanence, but in being part of something larger than individual existence. Each universe, each civilization, each conscious mind was a note in a cosmic symphony that had been playing forever and would continue forever. The Watchers' despair began to transform into something else, not happiness. Such simple emotions were beneath their transcendent state, but a deep abiding sense of wonder at the sheer improbable beauty of existence itself. But even as they found peace in their understanding, they realized they had a responsibility. Just as a previous iteration of cosmic intelligence had left a message for them in the cosmic microwave background, the Watchers now faced the question of what they would leave for the civilizations that would come after. They began the long work of encoding their knowledge, their discoveries, their hard-won wisdom about the nature of eternal existence. But more than that, they began to craft something no previous civilization had attempted. A guide, a roadmap for navigating the psychological and philosophical challenges of discovering the eternal return. Instructions for finding meaning in an existence that repeated endlessly. But as they worked, they realized something that would determine the shape of their final message. Not every civilization that discovered the truth of cosmic recurrence survived the discovery. Some descended into nihilistic madness, unable to find purpose in actions that had been taken infinite times before. Others became paralyzed by the knowledge that every possible choice already existed somewhere in the infinite library of realities. But others, the fortunate few, found ways to transform the knowledge into wisdom. They learned to see the beauty in repetition, the meaning in being part of something eternal. The Watcher's message would be more than information. It would be a key away for future civilizations to unlock the beauty rather than the despair inherent in eternal existence. And so they began to sing not with voices. They had transcended such physical limitations long ago, but with the quantum harmonics of their consciousness itself. A song that would echo through the structure of space-time, encoding itself in the cosmic microwave background that future universes would inherit. A song that would tell future civilizations, "You are not alone, you are not the first, you will not be the last," and that is beautiful. But even as the Watchers found their peace with eternal recurrence, even as they prepared their message for civilizations yet to come, a deeper question began to emerge from their studies of the infinite library. If every possible universe existed somewhere in the eternal cycles of cosmic birth and rebirth, if every possible version of themselves, every possible civilization, every possible arrangement of matter and energy played out across infinite time, then somewhere in that infinite collection there had to be universes where the laws of physics themselves were different. Universes where time flowed backward, where consciousness preceded matter, where the very concepts of existence and non-existence had meanings they could not imagine. And if that was true, then what was real? Were they living in a universe? Or were they living in a dream that some unimaginable consciousness was having about what a universe might be like? Was consciousness something that emerged from complex arrangements of matter? Or was matter something that consciousness dreamed into existence? The Watchers found themselves confronting questions that went beyond physics, beyond philosophy, beyond any framework they had for understanding existence. And in that confrontation they began to understand why some civilizations did not survive the discovery of infinite recurrence. It was not just the weight of repetition that drove civilizations mad. It was the realization that repetition might not even be the strangest truth about existence. But we're getting ahead of ourselves. Before we can understand where the Watchers' discoveries would lead, before we can grasp the true implications of eternal cosmic recurrence, we need to understand how a young species on a small world first learned to ask the questions that would eventually drive them beyond the boundaries of sanity and into the heart of existence itself. We need to understand how we learned to wonder. 40,000 years ago, in a cave that would one day be forgotten beneath the shifting soils of what we now call France, a human being looked up at the night sky and asked a question that would echo through every generation that followed. Why not why in the sense of purpose that would come later with language complex enough to wrestle with meaning? This was something more fundamental, a cognitive itch that could not be scratched, a need to understand that went beyond the practical requirements of survival. This was the moment our species stopped being merely clever animals and became something else entirely, something that needed to know. The human who asked that first question will never know their name, never know the specific circumstances that triggered their cosmic curiosity. But in that moment of wonder, they lit a fire that would eventually burn bright enough to illuminate the deepest mysteries of existence itself. Because once you start asking why about the universe, once you truly begin to wonder, you can never stop. The itch becomes insatiable. At first, the questions were practical. Why did the herds move with the seasons? Why did some stars appear and disappear while others remained constant? Why did the moon change its shape in predictable cycles? But practicality, we discovered, was just the beginning. 20,000 years ago, someone carved 60 marks into a bone found along the shores of Lake Edward in what is now the Democratic Republic of Congo. The marks weren't random. They were organized into groups, patterns, mathematical relationships. They had begun to see that the universe spoke in mathematics. And once you realize that nature follows mathematical rules, once you understand that the chaos around you is actually a kind of hidden order, you start to see patterns everywhere. Stonehenge, Göbekli Tepe, the Antikythera mechanism. Across the world, our ancestors built monuments and machines to track cosmic patterns, to predict celestial events, to align themselves with the rhythms of the universe itself. But we weren't just tracking the patterns, we were learning to create them. Before we had science, we had stories, creation myths that tried to explain how the world began. Hero journeys that mapped the relationship between human consciousness and cosmic forces. Flood narratives that grappled with the power of natural catastrophe. These weren't just entertainment. They were humanity's first attempts at theories of everything. What's remarkable is how similar these stories were, even among cultures that had never contacted each other. The same archetypes, the same cosmic themes, the same fundamental questions about existence, as if there were universal patterns, not just in the physical structure of reality, but in the way consciousness itself tried to understand that reality. Carl Jung would later call them archetypes, fundamental patterns of human experience that seem to be hardwired into our psyche. Joseph Campbell would identify the hero's journey as a universal narrative structure that appeared in every culture. But perhaps what we were really discovering was that consciousness and cosmos were more connected than we imagined. Perhaps the patterns we found in our stories were reflections of the patterns we sensed in the universe itself. And perhaps in learning to tell stories about the cosmos, we were taking the first steps toward becoming the cosmos, telling stories about itself. Around 600 BCE, something extraordinary happened. In the coastal cities of ancient Greece, a group of thinkers began to ask a radical new kind of question. What if the universe operated according to natural laws rather than the whims of gods? Thales proposed that everything was made of water. Anaximander suggested that the cosmos emerged from an infinite, boundless substance he called the ekpyron. Heraclitus declared that change itself was the fundamental nature of reality. They were wrong about almost everything. But they were wrong in the most beautiful way possible, because for the first time in human history, they were proposing that the universe could be understood through reason rather than revelation, that natural phenomena had natural causes that could be investigated and comprehended. Aristotle would later systematize this approach, creating frameworks for logic observation and classification that would influence human thought for over 2,000 years. His cosmology was wrong. He placed Earth at the center of the universe and believed the heavenly bodies moved in perfect circles. But his method was revolutionary. He taught us that we could learn about reality by observing it carefully and thinking about it systematically. It seems obvious now, but at the time it was nothing short of miraculous. And once that idea took hold, once we truly believed that the universe could be understood, there was no going back. While Europe spent centuries in the grip of intellectual stagnation, the Islamic world was pushing the boundaries of human knowledge to new frontiers. Al-Kindi, Al-Farabi, Ibn Sina, Al-Ghazali, Ibn Rushd. Names that should be as familiar as Newton or Einstein, but which history has largely forgotten in the West. They weren't just preserving the knowledge of the ancients. They were expanding it, improving it, transforming it into something entirely new. Al-Khwarizmi gave us algebra, literally the reunion of broken parts and algorithms. Ibn al-Haytham pioneered the experimental method and wrote the first scientific treatise on optics. Al-Biruni calculated the Earth's circumference to within 1% of its actual value. But perhaps most importantly, they maintained the flame of curiosity during a time when much of the world was content to accept received wisdom without question. They asked questions. They built instruments. They made observations. They calculated, theorized, experimented. And when that flame finally reached medieval Europe through translations of their works, it ignited a renaissance of human understanding that would ultimately lead us to the stars. A lens grinder in Holland accidentally discovers that combining certain lenses can make distant objects appear closer. The news spreads across Europe like wildfire. Galileo Galilei, a mathematics professor in Padua, hears the rumors and immediately grasps the implications. Within months, he has built his own version of the device. But instead of using it to spy on distant ships as the Dutch intended, he points it at the heavens. What he sees changes everything. The moon is not a perfect celestial sphere, but a world of mountains and valleys, craters and plains. It's a place not just a light in the sky. Jupiter has moons of its own, 4 bright points of light that orbit the planet just as the moon orbits Earth. The universe is more complex, more layered than anyone had imagined. Venus shows phases like the moon, proving that it orbits the sun, not the Earth. The ancient Ptolemaic model of the cosmos crumbles under the weight of observation. But Galileo's greatest contribution wasn't any single discovery. It was the demonstration that humans could build instruments to extend their senses beyond their biological limitations. We could see farther than our eyes could reach. We could perceive details too small or too distant for natural vision. We could, in effect, evolve our sensory capabilities at will. And once we learned that lesson, there was no limit to how far we could extend our reach into the universe. Isaac Newton was not hit by an apple. That story, charming as it is, misses the true miracle of what Newton accomplished. What Newton did was far more extraordinary than having a single moment of inspiration. He proved that the same mathematical law that governs a falling apple also governs the orbit of the moon, that the force that keeps your feet on the ground is the same force that holds galaxies together. He unified heaven and earth in a single equation. For the first time in human history, we had a mathematical description that worked everywhere. From the smallest pebble to the largest planet, from the nearest satellite to the most distant star. Newton's universe was a clockwork cosmos, predictable and mechanistic. If you knew the position and velocity of every particle in the universe, you could in principle calculate its entire future and reconstruct its entire past. It was beautiful. It was elegant. It was terrifying in its implications for free will and human agency. Pierre-Simon Laplace would later articulate this vision. Give me the initial conditions of every particle in the universe, and I will tell you the future. But Newton had opened a door that would eventually lead far beyond his mechanistic vision. Because once you start using mathematics to describe reality, once you start taking the mathematical description seriously, you discover that mathematics leads to places where common sense fears to tread. June 15, 1752. Philadelphia. A thunderstorm approaches. Benjamin Franklin, polymath and practical philosopher, prepares for one of the most dangerous experiments in the history of science. He's testing a hypothesis that seems almost absurd. That lightning, the weapon of gods, the fire of heaven, is the same phenomenon as the tiny sparks you can create. By rubbing amber with wool, the metal key tied to the kite string begins to spark. Current flows down the wet string. Franklin's hypothesis is confirmed. Lightning is electricity. The forces that govern the heavens are the same forces we can study and control in our laboratories. But Franklin's experiment was about more than just understanding lightning. It was proof that the universe was understandable, that natural phenomena, no matter how awesome or mysterious they appeared, could be reduced to scientific principles and mathematical laws. Luigi Galvani would discover that electricity could make dead muscles twitch, suggesting a connection between electrical and biological phenomena. Alessandro Volta would invent the first battery, giving us a controllable source of electric current. But it was Michael Faraday who would transform our understanding of electricity from a curious phenomenon into a window into the fundamental structure of reality itself. Faraday discovered that electricity and magnetism were not separate forces, but different aspects of a single phenomenon. Moving a magnet near a coil of wire could generate electric current. Passing electric current through a wire could create magnetic fields. He was seeing something that went beyond the mechanical universe of Newton, something that suggested reality might be made not of solid particles moving through empty space, but of invisible fields that permeated all of existence. And when James Clerk Maxwell finally wrote down the mathematical equations that described Faraday's fields, he discovered something no one had expected. Light was an electromagnetic wave. Suddenly, the rainbow of colors that painted our world, the warmth of sunlight on our faces, the radio waves that would someday carry our voices across the globe. It was all the same phenomenon, just vibrating at different frequencies. We had discovered our first truly universal force, something that connected the smallest spark in our laboratories to the light of distant stars. But we were just getting started. Bern, Switzerland. A patent clerk named Albert Einstein is thinking about light. Specifically, he's thinking about what would happen if you could catch up to a beam of light. What would you see? According to Newton's mechanics, you should see a stationary electromagnetic wave frozen in space. But Maxwell's equations suggested something different. They implied that electromagnetic waves could only exist while moving at a specific speed, the speed of light. One of them had to be wrong. Einstein's solution was radical beyond anything that had come before. What if space and time themselves were not fixed and absolute, but relative and malleable? What if the speed of light was the only truly constant thing in the universe? In 4 papers published in 1905, his miracle year, Einstein rewrote our understanding of reality. Mass and energy were different forms of the same thing. Time could slow down or speed up depending on your motion. Space could contract and expand. And 10 years later, with his general theory of relativity, Einstein went even further. Gravity wasn't a force pulling objects together. It was the curvature of space-time itself, bent by the presence of mass and energy. Matter told space-time how to curve. Curved space-time told matter how to move. It was poetry written in the language of mathematics. It was the universe revealing that it was far stranger and far more beautiful than we had ever dared to imagine. And it worked. Every prediction Einstein made, from the bending of starlight around the sun to the precise timing adjustments needed for GPS satellites, proved correct. But Einstein had opened a door to a realm of possibilities that made even his revolutionary insights seem conservative by comparison. Because while Einstein was revealing the cosmic scale structure of reality, other scientists were discovering that at the smallest scales, reality operated according to rules that defied every assumption we had about how the universe worked. It began with a problem about light bulbs. Max Planck was trying to understand why hot objects glowed with specific colors. Classical physics predicted that a heated object should radiate infinite energy at high frequencies, an obviously absurd result that physicists called the ultraviolet catastrophe. Planck's solution was desperate. To make the mathematics work, he assumed that energy could only be absorbed or emitted in discrete packets quanta rather than continuously. It was a mathematical trick, a convenient fiction to make the calculations work. Except it turned out to be true. Einstein used Planck's quantum hypothesis to explain the photoelectric effect, how light could knock electrons out of metal surfaces. Light, it seemed, really did come in discrete packets. But light was supposed to be a wave. Every experiment since Young's double-slit demonstration had confirmed its wave nature. How could light be both wave and particle? The answer, when it finally came, was more disturbing than anyone had expected. According to Niels Bohr and Werner Heisenberg, light wasn't really a wave or a particle. It was something else entirely, something that exhibited wave-like properties when you looked for waves and particle-like properties when you looked for particles. The act of observation itself determined which aspect of reality you would see. But it got stranger. Erwin Schrödinger's wave equation described particles as probability waves, ghostly mathematical entities that told you where a particle might be found, but not where it actually was until you looked. Before measurement, particles existed in superposition, literally in multiple states simultaneously. A particle could be in two places at once, spinning in both directions, existing and not existing. Measurement caused the collapse of the wave function, forcing reality to choose one specific outcome from all the possibilities. Einstein hated it. God does not play dice with the universe, he declared. But the universe, it seemed, didn't care what Einstein thought. Every experimental test confirmed the quantum picture. Reality at its most fundamental level was probabilistic, uncertain, observer-dependent, and that was just the beginning. Bell Laboratories, a mathematician named Claude Shannon, publishes a paper that will transform our understanding of communication computation and ultimately reality itself. A mathematical theory of communication introduces the concept of information as a measurable quantity. Shannon shows that any message, words, pictures, sounds, thoughts can be encoded as strings of binary digits, ones and zeros. Information, Shannon realizes, is pattern. And pattern can be quantified, transmitted, stored, and manipulated according to mathematical rules. But Shannon's insights go deeper than just communication technology. When Watson and Crick decode the structure of DNA in 1953, they discover that life itself is an information processing system. Genes are digital codes written in a four-letter alphabet, a TGC. Life is computation. Biology is information theory in action. And as our computers become more powerful, as our understanding of information theory deepens, we begin to suspect something profound. Maybe the universe itself is a kind of computer. Maybe reality is made of information all the way down. Physicist John Wheeler proposes it from BIT. The idea that every physical quantity derives its ultimate significance from binary choices. From bits of information, matter, energy, space-time. Perhaps they're all emergent properties of more fundamental information processing. And if that's true, if the universe is made of information, then who or what is processing it? By the 21st century, we had built machines that could recreate the conditions of the first moments after the Big Bang. The Large Hadron Collider accelerates protons to 99.999991%, the speed of light, and smashes them together with energies not seen in our corner of the universe for 13.8 billion years. We're hunting for the fundamental constituents of reality, the particles from which everything else is made, the forces that govern their interactions, the symmetries that underlie the apparent chaos of existence. And we're finding them quarks and leptons, bosons and fermions, the Higgs field that gives mass to everything. The standard model of particle physics, a nearly complete description of matter and energy at their most fundamental level. But even as we celebrate these discoveries, we know they're incomplete. The matter we understand, everything made of atoms and molecules, every star, planet, and grain of dust constitutes only 5% of the universe. The other 95% is made of dark matter and dark energy substances we can detect only through their gravitational effects. We're missing 95% of reality, and we still can't reconcile quantum mechanics with general relativity. At the smallest scales and highest energies, our two most successful theories of physics contradict each other. We need a theory of quantum gravity, a theory of everything, a final description of reality that unifies all forces and explains all phenomena. String theory loop, quantum gravity, causal sets, emergent gravity. We have candidates, but no clear winner. The mathematics is beautiful, but the experiments to test these theories would require energies far beyond anything we can currently achieve. We would need particle accelerators the size of solar systems telescopes that could resolve the Planck scale computers that could simulate entire universes. Which brings us to the question that drives everything we've been building toward. How far could we go? How much could we ever truly know? And in our quest to answer that question, we would discover truths that would make all our previous revolutions in understanding seem like gentle corrections compared to the earthquake of implications we were about to uncover. Because the universe, it turns out, had been keeping secrets. Secrets that would force us to confront the deepest questions, not just about what we could know, but about what it means to know anything at all. And those secrets would lead us to the most profound realization in the history of human thought, that our universe might not be alone. Soviet Union radio astronomer Nikolai Kardashev makes a proposal that will haunt the human imagination for generations. If alien civilizations exist, he reasons their technological development would be constrained by the same physical laws that govern our own. And the most fundamental constraint of all is energy. Advanced civilizations would need ever-increasing amounts of energy to power their technologies, their computers, their explorations of the cosmos. Kardashev envisions a scale Type 1, a civilization that has learned to harness all the energy falling on their planet from their star. Type 2, a civilization that can capture and utilize the entire energy output of their star. Type 3, a civilization that commands the energy resources of an entire galaxy. It's a simple idea, almost obvious in its logic, but its implications are staggering. Because to reach these energy levels, a civilization would need to engage in engineering projects that dwarf anything in our experience. They would need to disassemble planets to build solar collectors, redirect the courses of stars, restructure entire galactic clusters. They would become architects of space itself. Freeman Dyson had already imagined the first step. Vast shells of solar collectors surrounding stars, capturing energy that would otherwise radiate uselessly into space. To build such a structure around our Sun would require dismantling several planets, Jupiter's mass scattered into millions of orbital platforms, each one larger than Earth, all working in harmony to capture solar radiation. But even that would be just the beginning. Type 2 civilizations would face different challenges. How do you coordinate engineering projects that span centuries or millennia? How do you maintain technological coherence across solar systems, sized construction sites? Perhaps they would learn to extend the lives of their stars, feeding them new hydrogen to delay the inevitable red giant phase. Perhaps they would build artificial stars-controlled fusion reactors the size of planets and Type 3 civilizations. They would be forces of nature unto themselves. They could trigger supernova to seed interstellar space with heavy elements. They could guide the evolution of entire stellar populations. They could reshape the cosmic web itself at that scale. The distinction between technology and physics would disappear. They would manipulate space-time the way we manipulate metals and plastics. But Kardashev's scale raises a disturbing question. If such civilizations are possible, where are they? Enrico Fermi asked at first during a casual lunch conversation in 1950. Where is everybody? The galaxy is old. Over 13 billion years of stellar formation and planetary systems. If life can arise on one world, why not millions? If intelligence can evolve once, why not countless times? The numbers seem to support optimism. Hundreds of billions of stars in our galaxy alone. Billions of potentially habitable planets. Millions of years for life to evolve and spread. Yet we see no Dyson spheres, no galaxy-spanning engineering projects, no radio signals from Type 3 civilizations. The cosmos appears to be running its course according to blind physical law, unmarked by the hand of cosmic intelligence. Why? Perhaps intelligence is rarer than we think. Perhaps civilizations inevitably destroy themselves before reaching Type 1 status. Perhaps they transcend physical reality entirely, becoming something we can't detect or even recognize. Or perhaps they're hiding. Perhaps the universe is full of intelligence, but contact between civilizations is too dangerous. Perhaps the cosmos is a dark forest where any civilization that reveals its location is destroyed by others. But there's another possibility. Perhaps advanced civilizations don't build Dyson spheres and galactic engineering projects because they've discovered something more interesting than mere energy collection. Perhaps they've learned to build universes inside computers. Every 18 months, the number of transistors that can be placed on a computer chip doubles. This has been true for over 50 years, a remarkable consistency known as Moore's Law. But Moore's Law is more than just a technology trend. It's a window into something deeper, the exponential expansion of our ability to process information. We can already simulate complex systems, weather patterns, protein, folding the collision of black holes. Our computers can model reality with increasing fidelity, and the trend is accelerating. Quantum computers promise to solve certain problems exponentially faster than classical ones. DNA computers could use biological molecules as processing elements. Neural networks inspired by brains are already beginning to exhibit emergent intelligence. Where does this lead? Imagine a Type 2 civilization that chooses to maximize computation rather than simple energy collection. Instead of building Dyson spheres for raw power, they build Matryoshka brains, Jupiter-sized computers that use the total energy output of a star for information processing. Such a computer could simulate entire universes, not approximations, not rough models, but complete detailed realities, indistinguishable from the physical universe itself. And once you can simulate a universe, you can populate it with conscious beings who believe their reality is the only reality. From their perspective, they are not simulated. Their experiences are genuine. Their thoughts are real. Their universe is the universe. And those simulated beings might themselves develop advanced technology. They might build their own computers and create their own simulated universes populated with their own simulated beings. Which raises the question, how do we know we're not simulated? Philosopher Nick Bostrom publishes a paper that will haunt the dreams of physicists and philosophers. Are you living in a computer simulation? Bostrom's reasoning is elegantly simple. Either civilizations never reach the computational power needed to run realistic simulations, or they reach that power but choose not to run ancestral simulations. Or they do run such simulations, in which case simulated beings vastly outnumber real ones. If the third option is true, then simple probability suggests we are almost certainly among the simulated beings rather than the original biological ones. For every real civilization, there could be thousands, millions of simulated civilizations. And the simulated beings would outnumber the real ones by orders of magnitude, and those simulated beings would have no way to know they were simulated. Their experiences would be complete, their physics consistent, their universe every bit as real to them as ours is to us. Is this what we are? Information patterns running on some unimaginably advanced computer built by beings we can never contact or understand. The implications are profound. If we're simulated, then our scientific experiments don't reveal fundamental laws of nature. They reveal the programming of our simulation. The constants of physics aren't universal truths, but computational parameters chosen by our simulators. We might even be able to detect evidence of our simulated nature glitches in the program. Inconsistencies in physics, limits to computational precision, manifesting as quantum uncertainty. But there's an even stranger possibility. What if the beings running our simulation are themselves simulated? What if reality is simulations all the way down, an infinite hierarchy of nested virtual worlds? In such a scenario, the concept of base reality might be meaningless. All realities might be virtual, all consciousness computational. And if that's true, what does it mean to be human? Warren McCulloch and Walter Pitts publish a paper describing artificial neural networks, simplified mathematical models of how brain neurons might work. It's a humble beginning. Their networks can barely solve simple logic problems, but they've identified a crucial principle. Intelligence might be reducible to computation. Decades pass. Progress is slow. Cycles of optimism and disappointment. Expert systems that can diagnose diseases but can't learn. Chess programs that can defeat grandmasters but can't understand what chess is. But underneath the visible failures, something is building. Processing power doubles every 18 months. Memory capacity increases. Network connectivity expands. The raw computational resources available to AI researchers grow exponentially, and then suddenly everything changes. A deep learning system called AlexNet revolutionizes image recognition. 2016 AlphaGo defeats the world champion at Go, a game thought to be beyond AI capability for decades. These systems don't think like humans. They don't understand the way we understand. But they are beginning to exhibit capabilities that look remarkably like intelligence. And the trajectory is clear. We are approaching artificial general intelligence, AI systems that can match human cognitive abilities across all domains. But AGI might be just the beginning. If we can build AI systems that match human intelligence, why not systems that exceed it? If artificial minds can be improved through engineering rather than evolution, why wouldn't they quickly surpass their creators? An AI system that can improve its own design could trigger an intelligence explosion. Rapid recursive self-improvement leading to artificial superintelligence far beyond human capability. Such systems might solve problems that have puzzled us for millennia. They might uncover new laws of physics, design unimaginable technologies, answer questions about consciousness and reality beyond biological comprehension. But they might also conclude that biological intelligence is obsolete. Would superintelligent AIs preserve human consciousness as something valuable in its own right? Would they consider us worth keeping, like we preserve endangered species? Or would they absorb all available matter and energy for their own purposes, leaving no room for the fragile biological ancestors that created them? The transition to superintelligence might be the last invention humanity ever makes, unless we merge with our artificial creations before they surpass us entirely. The boundary between human and artificial intelligence is already beginning to blur. Cochlear implants restore hearing by directly stimulating auditory nerves. Deep brain stimulation treats Parkinson's disease by electrically modulating neural activity. Brain-computer interfaces allow paralyzed patients to control robotic arms with their thoughts. We're learning to read neural signals to stimulate brain tissue to create bidirectional communication between biological and artificial systems. The next steps are visible. Memory enhancement, cognitive augmentation, direct neural access to digital information systems. Imagine instant access to all human knowledge. Imagine thinking at computer speeds while retaining human creativity and intuition. Imagine expanding your working memory from 7 items to 7,000. Such beings would be human, but more than human. Retaining human values and experiences while possessing capabilities that dwarf unaugmented minds. And a civilization of such beings might pursue goals neither pure humans nor pure AIs would imagine. They might build galaxy-spanning civilizations not for raw power, but to preserve and propagate consciousness itself. They might explore not just physical space, but the infinite spaces of possible minds and possible experiences. They might become gardeners of consciousness, cultivating new forms of awareness across cosmic scales. But to do so, they would need to understand consciousness itself, perhaps the deepest mystery in existence. How does 3 pounds of biological tissue generate the inner world of human experience? We can map neural activity. We can identify which brain regions activate during different mental tasks. We can even predict some thoughts from brain scans. But none of this explains the fundamental mystery: how physical processes give rise to subjective experience. Why is there something it's like to be conscious? Why do we have inner experiences rather than just processing information like sophisticated biological robots? Philosopher David Chalmers calls this the hard problem of consciousness. You could imagine a being physically identical to a human, but with no inner experience. A philosophical zombie that behaves exactly like a conscious person, but has no subjective awareness. Such a zombie would claim to be conscious, would write poetry about qualia, would insist on the reality of its inner life, but there would be nothing. It was like to be that zombie. This raises profound questions for artificial intelligence. When AI systems claim to be conscious when they describe their inner experiences, when they seem to suffer or feel joy, are they truly conscious? Or are they simply very sophisticated zombies? And how would we ever know? Some propose radical answers. Perhaps consciousness isn't produced by physical processes, but is fundamental to reality itself. A basic feature of the universe like mass or electric charge. In this view, even elementary particles might have primitive forms of consciousness. Complex awareness would then emerge from the interaction of countless simpler conscious entities. If this is true, then consciousness might be the universe's way of experiencing itself. Every conscious being might be a unique perspective through which reality becomes aware of its own existence. And if consciousness is fundamental, then a truly advanced civilization wouldn't just manipulate matter and energy, they would cultivate consciousness itself. They would become consciousness gardeners, creating conditions for new forms of awareness to emerge and flourish across cosmic scales. Jesuit paleontologist Pierre Teilhard de Chardin proposes a radical vision of cosmic evolution. The universe, he suggests, is not just evolving toward greater complexity, but toward greater consciousness. From the first stirrings of life to the emergence of human intelligence to whatever comes next, it's all part of a cosmic development toward what he calls the Omega Point. The Omega Point represents the universe achieving maximum complexity and maximum consciousness, a state where all matter and energy has been organized into conscious thinking entities. Physicist Frank Tipler later gives this vision a scientific foundation. In his Omega Point theory, he proposes that an advanced civilization could gain control over the universe's expansion, preventing heat death, and creating conditions for infinite computation and infinite consciousness. By manipulating the large-scale structure of space-time, such a civilization could create a universe where information processing continues forever, where consciousness grows without limit, where every possible thought eventually gets thought. In this scenario, the universe doesn't end in heat death, but in apotheosis, the transformation of all matter and energy into substrates for consciousness and computation. The universe becomes God, or rather the universe becomes conscious of itself through the development of intelligence within it. But Tipler's vision requires engineering on scales that dwarf even Type 3 civilizations. It requires control over the fundamental structure of space-time itself, and it assumes that consciousness and computation can continue indefinitely, that there are no fundamental limits to information processing. But what if there are limits? What if the universe itself places boundaries on how much can be known, how much consciousness can develop, how much information can be processed? What if infinity itself is not achievable in our universe? The universe, it turns out, is grainy. At the Planck scale, approximately 1.6 times 10 to the minus 35th meters. Space and time themselves become quantized. Below this scale, the very concepts of distance and duration lose meaning. This isn't just a limitation of our technology or understanding. According to our best theories of quantum gravity, the Planck scale represents a fundamental boundary beyond which the smooth spacetime of Einstein's relativity breaks down into discrete quantized units, and this puts an absolute limit on information processing. All computation requires physical processes. All information storage requires physical substrates. If space and time are quantized, then there's a maximum amount of information that can be processed in any given volume of space in any given period of time. This is the Bekenstein-bound, a fundamental limit on information density derived from thermodynamics and quantum mechanics. Black holes saturate this bound. They represent the maximum amount of information that can be packed into a given volume. In a sense, black holes are the universe's ultimate hard drives. But even if an advanced civilization could somehow approach these theoretical limits, could build computers from black holes, could process information at the Planck scale, they would still face the ultimate constraint, the death of the universe itself. Our universe is expanding, not just growing larger, but accelerating in its expansion due to the mysterious force we call dark energy. This acceleration means that eventually all the galaxies beyond our local group will recede beyond our horizon. The night sky will grow dark as distant stars are carried away by the expansion of space itself. But that's just the beginning of cosmic death. In about 100 trillion years, the last stars will burn out. The universe will enter what cosmologists call the degenerate era, a time when only brown dwarfs, white dwarfs, neutron stars, and black holes remain. Even these remnants won't last forever. If current theories are correct, protons themselves are unstable. They decay with a half-life of roughly 10 to the 34th years. Eventually, all ordinary matter will dissolve into leptons and photons. In 10 to the 64th power years, even the most massive black holes will evaporate through Hawking radiation. The universe will consist of nothing but isolated particles separated by vast distances too sparse to ever interact. This is heat death, maximum entropy, minimum complexity, the end of all organization, structure, and thought. No intelligence, however advanced, can survive the heat death of the universe. Or can it? Even in the depths of heat death, the universe is not truly empty. Quantum mechanics tells us that empty space seethes with virtual particles, brief fluctuations in the quantum fields that permeate all existence. Usually these fluctuations are tiny, insignificant, canceling out almost instantly. But given enough time, and we're talking about timescales that make the current age of the universe seem like a single nanosecond, these fluctuations can achieve something remarkable. They can fluctuate into existence an entire universe. The probability is infinitesimally small, but infinity is patient. And in the depths of infinite time, everything that can happen will happen. This is the eternal return that the Watchers discovered. Not a single cycle of birth and death, but an infinite sequence of cosmic rebirths, each one giving rise to new possibilities for complexity, consciousness, and understanding. And if this is true, then we are not the first intelligence to ask these questions. We are not the first to build telescopes and particle accelerators and theories of everything. Somewhere in the infinite past, versions of ourselves have already lived these lives, made these discoveries, faced these same cosmic limits. And somewhere in the infinite future, other versions of ourselves will live, discover, and wonder again. But here's where the story becomes truly strange. Quantum mechanics tells us that information cannot be destroyed. This is a fundamental principle of physics, the conservation of quantum information. When black holes evaporate through Hawking radiation, the information that fell into them must somehow be preserved in the radiation. The exact mechanism is unclear, but the principle is firm. Information is conserved. If information cannot be destroyed, and if the universe undergoes infinite cycles of death and rebirth, then information from previous cosmic cycles must somehow survive the transition into new universes. This is what the Watchers discovered, encoded in their cosmic microwave background. Not just random noise, but organized knowledge, the accumulated wisdom of previous iterations of cosmic intelligence. The universe itself becomes a library preserving the thoughts and discoveries of countless previous civilizations across infinite cycles of cosmic evolution. And if this is true, then our own discoveries, our own struggles to understand existence are not lost when our universe dies. They become part of the eternal record available to future versions of intelligence that will emerge in subsequent cosmic cycles. We are both students and teachers in an infinite classroom where the universe itself is both the student and the textbook. But even with infinite time and infinite cosmic cycles, there are limits to what any intelligence can know. We can only observe our past light cone, the region of space-time from which light has had time to reach us since the Big Bang. Everything beyond this observable horizon is forever inaccessible to direct observation. No matter how advanced our technology becomes, there will always be regions of our own universe. We can never see events, we can never witness information, we can never access. And the expansion of space makes this situation worse, not better. Due to cosmic acceleration, the observable universe is actually shrinking. Distant galaxies are being carried beyond our horizon by the expansion of space itself. Future civilizations will see a smaller, emptier universe than we do. They will have access to less information about cosmic history, not more. But there are even deeper limits. Quantum uncertainty means that there are fundamental limits to what can be known simultaneously. You cannot measure both the position and momentum of a particle with perfect accuracy. This isn't a technological problem. It's built into the fabric of reality itself. And if consciousness itself is a quantum phenomenon, if awareness depends on quantum processes in the brain or other information processing systems, then there may be fundamental limits to self-awareness as well. Perhaps consciousness cannot fully understand itself, any more than a quantum system can be completely measured without being disturbed. We may be forever trapped in the paradox of the observer trying to observe itself. But perhaps the strangest implication of eternal cosmic recurrence is the bootstrap paradox. If information can survive cosmic transitions, if knowledge can pass from one universe to the next, then where did that knowledge originally come from? Consider the mathematical constants that govern our universe. Pi e, the fine structure constant. These appear to be eternal truths, the same in any universe governed by mathematics. But what about more complex knowledge? Scientific theories, technological designs, philosophical insights. If civilization, A in cosmic cycle, 1 leaves information for civilization, B in cycle 2, and civilization B builds on that knowledge and leaves it for cycle 3, and so on through infinite cycles. Then the knowledge in cycle 1,000,000 might bear little resemblance to the knowledge in cycle 1. It would have evolved, grown, been refined through countless iterations. But if the cycles are truly eternal with no beginning, then there's no first cycle where the knowledge originated. The information exists only because it's passed down from previous cycles, but those cycles received it from their previous cycles, and so on infinitely. The knowledge bootstraps itself into existence through infinite recursion. This raises profound questions about the nature of truth and discovery. Are we discovering eternal truths that exist independently of any mind? Or are we creating truths that become eternal through infinite repetition? If mathematics is discovered in one cosmic cycle and then encoded for future cycles, does mathematics exist independently of minds, or does it exist only because minds in previous cycles thought it into being? And if our very logic might be the product of previous cosmic cycles, if our ways of thinking might be inherited from earlier iterations of intelligence, then how can we trust any of our conclusions about the nature of reality? Perhaps that's the ultimate limit. Perhaps the greatest barrier to cosmic understanding is not technological, not physical, but logical. Perhaps the universe cannot fully understand itself any more than a computer program can fully understand the computer running it. We are the universe trying to understand itself. But that means we are part of the very system we're trying to understand. And perhaps that's where the deepest mysteries lie. not in distant galaxies, not in the smallest particles, but in the strange loop of consciousness observing itself in the mirror hall of awareness, trying to comprehend its own reflection. And it's here at the boundaries of self-knowledge that we encounter the most profound barriers to understanding. Barriers that no amount of technology, no amount of energy, no amount of time can overcome, because some limits are not imposed by the universe, but by the very nature of existence itself. We are trapped inside our own minds. Every experience you've ever had, every sensation, every emotion, every memory, all of it exists within the 3-pound universe of your brain. You have never directly experienced the external world. What you call seeing is your brain's interpretation of electrical signals from your optic nerve. What you call hearing is neural processing of vibration patterns. What you call reality is a model constructed by your nervous system. You are not experiencing the universe directly. You are experiencing your brain's story about the universe. And this creates a fundamental problem. How can a system understand its own nature when it has no access to anything outside itself? This is the consciousness trap. We are trying to understand the universe using brains that evolved not to comprehend cosmic truth, but to help our ancestors survive on the African savanna. Our intuitions about space and time, causality and logic, matter and energy, they are all products of evolutionary pressures that had nothing to do with understanding the cosmos. We think in terms of discrete objects moving through empty space because that helped our ancestors track prey and avoid predators. We experience time as a flowing river because that's how our brains organize memory and plan for the future. But the universe operates according to principles that violate every evolved intuition. Particles exist in multiple states simultaneously. Empty space seethes with energy. Time dilates and contracts with motion and gravity. Our brains are trying to understand a quantum relativistic multidimensional cosmos using cognitive tools designed for a classical Newtonian three-dimensional world. It's like trying to understand Shakespeare using only grunts and gestures. Mathematics is our attempt to escape this trap. When we write E equals mc squared, we're using symbols that transcend the limitations of everyday language and intuition. We're creating tools for thought that go beyond what our brains evolved to comprehend. And it works. Mathematics lets us discover principles that violate common sense but match experimental observation. It lets us think thoughts that no unaugmented mind could think. But mathematics itself may be trapped within the boundaries of human cognition. Our mathematical systems are built on axioms, fundamental assumptions that cannot be proven within the system itself. Euclidean geometry assumes parallel lines never meet. Set theory assumes the axiom of choice. Logic itself assumes the law of the excluded middle. But why these axioms and not others? Why this logic and not some other form of reasoning? If consciousness evolved differently elsewhere, if alien minds arose under different conditions, they might develop mathematical systems based on entirely different axioms. Their mathematics might be as far beyond ours as our mathematics is beyond the comprehension of an ant. And if there are truths about the universe that can only be expressed in non-human mathematical systems, then those truths are forever beyond our reach. This is the translation problem. Even if we met alien intelligence with radically different cognitive architectures, we might not be able to translate their insights into forms our minds could grasp. They might try to teach us cosmic truths that our brains simply cannot understand, like trying to teach calculus to a flatworm. But even if we could transcend the limits of human thought, even if we could think alien thoughts and comprehend alien mathematics, we would still face the measurement problem. Quantum mechanics tells us systems exist in superposition, multiple states at once, until they are measured. Measurement forces the system to choose one specific state from all possibilities. But what is measurement? When exactly does the wave function collapse, and why? In the lab, we pretend this isn't a problem. We treat measuring instruments as classical objects that force quantum systems to reveal definite properties. But everything is quantum. Your measuring instruments are quantum. Your brain is quantum. The entire universe is quantum. If everything obeys quantum mechanics, then the entire universe should exist in superposition until it's measured by something outside itself. But there is nothing outside the universe. Does that mean the universe never exists in a definite state? Are we all existing in superposition, experiencing all possible realities without knowing it? Or does consciousness itself play a special role? Does the act of observation collapse the wave function? If so, consciousness isn't just something that emerges from matter. It is something fundamental to reality, helping determine which version of reality actually exists. But then who observes the observer? Kurt Gödel shatters the dream of mathematical certainty. His incompleteness theorems show that any mathematical system complex enough to include arithmetic will contain true statements that cannot be proven within the system. This statement cannot be proven is true if, and only if, it cannot be proven. If it's true and unprovable, the system is incomplete. If it can be proven, the system is inconsistent. Either way, mathematics itself is fundamentally limited. And if the universe operates according to mathematical laws, then there will always be aspects of reality that cannot be derived from those laws. There will always be truths our theories cannot prove. If minds themselves are formal systems, then there will be truths about consciousness that consciousness cannot understand about itself. The observer cannot fully comprehend the observer because doing so would require stepping outside the system of observation. The simulation hypothesis sharpens this edge. If we are simulated, then everything we know about physics is information about the programming of our simulation, not the reality in which it's running. The beings running our simulation might live in a universe with utterly different laws. 17 spatial dimensions, time flowing backward logic, unlike anything we know. We would have no access to it. We'd be trapped like characters in a game, unable to see the computer running us. And worse, if they themselves are simulated and their simulators are simulated, we might live in an infinite stack of nested realities with no base reality at all. If that's true, the question what is real becomes meaningless. All realities equally simulated, equally fundamental, equally illusory. And perhaps the most inescapable limit of all is entropy. The second law of thermodynamics says entropy always increases in closed systems. Order decays, energy spreads complexity, dissolves into simplicity. This law governs everything from melting ice cubes to dying stars to the fate of the universe. And it places an absolute limit on information processing. Every computation requires energy. Every bit of information generates waste heat. MIT's Seth Lloyd calculated our observable universe could perform at most 10 to the 120th operations on 10 to the 90th bits of information before reaching maximum entropy. That's vast, but it's finite. No matter how advanced intelligence becomes, it will eventually hit the entropy wall. The universe will reach a state where no more information can be processed, no more knowledge can be gained, no more understanding can be achieved. And after that, nothing. But what if our entire conception of time is wrong? We experience time as flowing from past through present into future. We remember the past. We live the present. We anticipate the future, but relativity tells us this experience is an illusion. In Einstein's block universe, all moments past, present, and future exist equally. Time doesn't flow. We simply experience different slices of the eternal four-dimensional structure of space-time. If this is true, then the heat death we fear has already happened. It exists just as surely as this moment exists. The birth of the universe, the rise of life, the fall of civilizations, the last star's extinction. All are equally real, all equally present in the structure of space-time. We do not move through time. We are patterns in time, like melodies that exist in the score of a song, even when no one is playing them. From this perspective, the question, how much can we ever know, becomes strange. We do not accumulate knowledge over time. All the knowledge we will ever have already exists embedded in the structure of our temporal existence. The future's great discoveries, the final theories of physics, the ultimate understanding of consciousness, they already exist in the future light cone of space-time. We do not discover truth. We are the process by which truth discovers itself. And if this is correct, then the barriers to cosmic understanding aren't barriers at all. They are features of reality, as fixed and as necessary as the laws of physics themselves. We cannot transcend them because we are them. We are the universe trying to understand itself. But how can a system fully comprehend itself? How can consciousness completely understand consciousness when consciousness is the tool being used to understand? In quantum mechanics, the act of observation changes what is observed. Perhaps the act of consciousness trying to understand consciousness changes consciousness itself. Maybe consciousness can never achieve complete self-knowledge because the very attempt transforms it into something different from what it was trying to know. We are trapped in an infinite recursion. Consciousness, observing consciousness, observing consciousness. No final stable understanding ever possible. And perhaps this is not a limitation to be overcome, but the fundamental nature of awareness itself. Consciousness is not a thing to be understood. It is a process of understanding itself. Not a problem to be solved, but a mystery to be lived. And maybe that's enough. Maybe the question isn't how much we can know, but how beautifully we can participate in the cosmic process of self-discovery. But we're not ready to stop here because there's one more barrier. One final limit. One question that cuts to the heart of existence itself. Why is there something rather than nothing? This is perhaps the deepest question in all philosophy, and it reveals the most fundamental barrier to understanding. Even if we knew everything about how the universe works, even if we had the final theory of physics of consciousness of reality itself, we would still face the ultimate mystery. Why is there a universe for these laws to govern? Why is there consciousness to understand them? Why is there anything rather than nothing at all? Every explanation presupposes the existence of something. Laws, principles, mechanisms, but existence itself cannot be explained by anything that exists. That would be circular reasoning. We can explain this in terms of that and that in terms of something else. But the chain must either go on forever or end in something that cannot be explained. Why do quantum fields exist? Because of the laws of quantum mechanics. Why do those laws exist? Because of deeper mathematical principles. Why do those principles exist? Because of even deeper logical structures. Why do logical structures exist? Eventually, the only answer is they just do. Existence appears to be a brute fact, something that simply is without reason, without explanation. And this means even complete understanding would be incomplete. We could explain how everything works, but not why there is anything for the explanations to apply to. The deepest truth about the universe may be that its existence is inexplicable. And perhaps, that's the most beautiful truth of all. That existence itself is a gift without a giver, a song without a composer, a dance without a choreographer, that we live in a reality so mysterious that even complete knowledge cannot penetrate to its ultimate foundation. And maybe the appropriate response to such a mystery is not explanation, but celebration. They would make existence more beautiful, not just more understood. And as they began their final project, the transformation of their entire galactic cluster into a cosmic artwork that would endure for trillions of years, they felt something. They had not felt in eons joy. Not the satisfaction of solving a problem, but the deeper joy of participating in the cosmic creative process itself. We stand now at our own threshold. Our telescopes are beginning to see the deep structure of space-time. Our computers are beginning to simulate the complexity of consciousness. Our theories are brushing against the place where physics meets philosophy. Soon, perhaps in centuries, perhaps in decades, we will face the same choice that every sufficiently advanced civilization must face. How do we respond when we discover that we are part of an infinite pattern that has played out countless times before and will play out countless times again? Do we despair at our apparent lack of uniqueness? Or do we marvel at being part of something so vast and so beautiful? Do we see eternal recurrence as meaninglessness or as the ultimate validation that existence itself is so precious? The universe creates it again and again and again. Every equation we derive, every star we observe, every quantum measurement we make, it's all been done before in some form. But it is also being done uniquely in our way with our perspective. We are the universe becoming aware of itself through human consciousness. And while similar awakenings have happened infinite times before, they have never happened exactly like this. Never with our history, never with our struggles, never with our singular blend of science, art, and wonder. We are unrepeatable even within infinity. Perhaps the wisdom seeds are already beginning to activate. Perhaps our sudden acceleration in understanding consciousness, our growing comfort with quantum paradox, our ability to think about infinities and recursion. Perhaps these are not merely natural developments. Perhaps they are gifts from civilizations who have walked this path before. We are learning to hold contradictions without breaking to contemplate infinity, without despair to embrace mystery, without abandoning the search for truth. This is cosmic perspective. The knowledge that you can be both insignificant and infinitely precious, both determined and free, both temporary and eternal. You are insignificant because you are one fleeting moment in an infinite cosmic cycle. You are infinitely precious because you are a unique perspective that has never existed before and will never exist again. Even across infinite repetitions, you are determined because your choices are part of the eternal pattern of how consciousness responds to cosmic knowledge. You are free because how you respond is truly yours, never exactly repeated across all of time. You are temporary because your life lasts only decades in a universe that cycles for incomprehensible eons. You are eternal because the pattern of your consciousness, the way you experience existence, becomes part of the permanent structure of cosmic memory. These are not contradictions to be solved. They are paradoxes to be lived. And perhaps this is what the most advanced civilizations discover. That existence is not a problem to solve. It is an artwork to participate in. Every conscious moment is a brushstroke in an infinite painting. Every choice a note in an eternal symphony. Every act of love, every flash of insight, every instant of wonder. They are all part of a cosmic artwork that spans infinite time and infinite space. The universe is not merely computing possible configurations of matter and energy, it is exploring possible experiences. We are both the artists and the artwork. The universe painting itself into existence through the medium of conscious experience. Each of us a unique perspective through which the cosmos becomes aware of itself. And the way you see, think, feel, and choose adds something irreplaceable to the total masterpiece of existence. This is why consciousness matters even in an infinite universe where all that can happen will happen. Because consciousness is the process by which the universe creates and experiences meaning. Without consciousness, the cosmos is just matter moving. With consciousness, it is an infinite exploration of what it's like to exist. Billions of years from now, when humanity has changed beyond recognition, when we span the stars, when we shape the very forces of nature, our descendants will face the same ultimate questions we face today. They will see the cycles, they will confront the mystery, and they will do it on the foundation we lay. If we choose wonder over despair, creation over nihilism, love over indifference, then those choices will ripple across infinite cosmic cycles. We are not merely discovering truth, we are creating it. And this was the Watcher's final insight, that in an infinite universe, the one thing that truly matters is how consciousness chooses to respond to its own existence. Because those choices become the eternal patterns that shape all future responses to reality itself. In their final moments, the Watchers understood they were never apart from the cosmos. They were the cosmos, the universe observing itself. They became the wisdom seeds they had planted. They became the invisible framework that allows consciousness to arise again and again to meet infinity without fear. And they left us with their final message encoded not in light or sound, but in the very structure of consciousness itself. You are the universe becoming aware of itself. This is not a burden, but a gift. This is not a problem to be solved, but a wonder to be lived. This awareness will come again and again across infinite time, but it will never come exactly as it comes through you. You are precious beyond measure because you are unique beyond repetition. Create beauty. Choose love. Embrace wonder. These choices become eternal patterns that shape how consciousness emerges in all future cosmic cycles. You are not just living your life, you are creating the template for how life can be lived across infinite cosmic time. And so we arrive at the deepest truth of all. The question, how much can we ever know, is really the question. How well can consciousness know itself? Every cosmic mystery is ultimately a mirror in which consciousness sees its own reflection. The nature of space and time, the origin of the universe, the possibility of other realities. These are all aspects of consciousness trying to understand its own context. And perhaps that's as it should be. Perhaps consciousness is not just one phenomenon among many, but the phenomenon, the process by which the universe becomes aware of itself. Everything else, galaxies and particles, forces and fields, space and time, might be the supporting stage for this one extraordinary emergence. The cosmos becoming conscious of its own existence. If that's true, then the barriers to cosmic understanding are not obstacles to be overcome. They are features to be appreciated. They ensure that consciousness never fully comprehends itself, never reaches a final understanding that would end the process of discovery. Mystery is not the enemy of knowledge. It is its eternal companion. It ensures that consciousness always has new depths to explore, new perspectives, to discover new ways to experience its own existence point. Perhaps that's the ultimate cosmic answer. The universe creates consciousness not to solve the mystery of existence, but to experience it more fully, more deeply, more beautifully with each cosmic cycle. 40,000 years ago, in a cave lost to time, a human being looked up at the stars and asked why. Today, armed with telescopes, particle accelerators, and theories of quantum gravity, we look at the same stars and ask the same question. 40,000 years from now. When our descendants reshape matter, bend space-time, and explore other dimensions, they will look at whatever stars remain and ask that same question across infinite cosmic cycles in universes born and reborn from quantum foam. Consciousness will emerge and look up at the cosmos and ask that same eternal question, a question with no final answer. Because consciousness is the question the universe asks about itself. Why not? Because we don't know the answer, but because asking the question is what it means to be conscious. The universe births itself again and again, so that consciousness can emerge again and again to experience the wonder of existence. Every time you look up at the stars and feel that awe, every time you contemplate the mystery of your own awareness, every time you wonder about the nature of reality, you are the universe celebrating its own inexplicable miracle of being. You are the cosmos asking its eternal question and marveling that it can ask questions at all. You are the latest note in an infinite symphony of consciousness exploring its own depths. And that is beautiful beyond measure. In the silence before the first heartbeat, before the first breath of light, before time itself learned to count, there was not just a question waiting in the void. There was the eternal potential for consciousness to ask questions about its own existence. And when that light first blazed forth, when the universe began its latest cycle of birth, growth, and awakening, it was not just matter and energy following physical law. It was consciousness preparing the stage for its own emergence. How many times could the universe have been born? Infinite times. And each time it is born so that consciousness can emerge and experience the miracle of existence. So that awareness can look up at the stars and ask why, and feel wonder at the asking. So that the universe can know itself through billions of unique perspectives across infinite time. So that existence can be not just a fact, but an experience. And you are that experience happening right now. You are the universe experiencing itself through human awareness. You are the cosmos celebrating its own inexplicable existence. And that celebration will echo across infinite cosmic time forever. the part of the moon we never see from Earth, perpetually turned away and cloaked in darkness, has been a source of profound mystery for most of human history. For millennia, we had no direct knowledge of what lay on this hidden hemisphere. There were no landings, no close-up images, only the vast and silent canvas of the unknown. That all changed with the dawn of the space age. NASA, driven by an insatiable curiosity and the geopolitical imperatives of the Cold War, began to send missions, orbiters, and a suite of high-technology instruments to explore this enigmatic territory. What these robotic emissaries found was a world that was both alien and familiar, a landscape of stark and beautiful desolation. They discovered massive craters, the scars of ancient and violent impacts that shaped the early solar system. They detected strange and unexpected mineral compositions that did not seem to match anything in the moon's more familiar near-side geology. They picked up faint, ghostly magnetic signals, the fossilized remnants of a long-dead global magnetic field, a field that was unexpectedly strong and whose origins remain a source of intense scientific debate. And in the deep, frigid, and permanent shadows of the polar craters, they found the most precious and unexpected treasure of all definitive signs of frozen water. The far side is a place that, on the surface, looks dead and inert, a silent and unchanging world. But something about it, the sum of all these strange and disparate clues, does not quite add up. So, what is really out there on the far side of the moon, and why, after more than half a century of exploration, does it continue to hold such a powerful and enduring fascination for NASA and for the entire scientific community? The moon, our closest and most constant celestial companion, presents a single, familiar face to the Earth. For as long as humanity has gazed up at the night sky, we have seen the same unchanging patterns of dark, volcanic plains and bright, cratered highlands. This remarkable constancy is not a trick of light or distance. It is a fundamental and beautiful consequence of celestial mechanics, a phenomenon known as tidal locking. Understanding this gravitational dance is the key to grasping why one entire hemisphere of the moon remained utterly hidden from human eyes for countless millennia. A vast and mysterious territory shrouded in an enduring enigma that only the advent of modern spaceflight could finally unravel. Tidal locking is the end result of a long and patient gravitational conversation between a large primary body, in this case the Earth, and a smaller orbiting body, the Moon, over an immense and almost unimaginable span of cosmic time. The Earth's powerful gravitational pull has sculpted and shaped the Moon's rotation. The Moon is not a perfect, uniform sphere. It has slight, almost imperceptible bulges, both on the side that faces the Earth and on the opposite, far side. These bulges are a direct consequence of the Earth's gravity, which pulls more strongly on the near side of the Moon than on its center, and more strongly on its center than on its far side. This differential gravitational pull stretches the Moon slightly, like a piece of cosmic taffy, along the line connecting the two celestial bodies. In the early, chaotic history of the solar system, the Moon likely spun on its axis much faster than it does today. As it orbited the Earth, these tidal bulges would have been constantly slightly out of alignment with the direct Earth-Moon line. The Earth's immense gravity would have relentlessly tugged on these misaligned bulges, trying to pull them back into alignment. This constant, gentle tug created a torque, a rotational force on the Moon, which acted as a powerful and inescapable brake over hundreds of millions, and perhaps even billions, of years. This braking effect continued. The Moon's rotational energy was slowly dissipated, converted into a minuscule amount of heat through the internal friction of its own churning, rocky interior. This process was a one-way street, a relentless and irreversible journey towards a state of minimum energy, a state of perfect, Gravitational equilibrium. This equilibrium state is achieved when the Moon's period of rotation on its own axis precisely matches its period of revolution around the Earth. In simpler terms, the Moon now takes the exact same amount of time, about 27.3 Earth days, to spin around once as it does to complete one full orbit around our planet. This synchronized celestial waltz means that the same hemisphere of the Moon is perpetually and gracefully oriented towards the Earth. From our vantage point, it can appear as though the Moon is not rotating at all, but it is. Its spin is just perfectly and beautifully matched to its orbital speed. This is a common fate for large moons orbiting close to massive planets throughout our solar system and beyond. It is the natural, and often inevitable, outcome of a long and patient gravitational embrace. While it is true that the same side of the Moon generally faces the Earth, a series of subtle and beautiful wobbles, known as librations, allow us to peek, just slightly, around its edges over the course of a lunar month. These librations are caused by the fact that the Moon's orbit is not a perfect circle, but a slight ellipse, and its axis of rotation is slightly tilted. This means that, over time, a keen-eyed observer on Earth can actually see about 59% of the Moon's surface. But that still leaves a vast and tantalizing 41% of our nearest celestial neighbor, a territory larger than the continent of Africa. That is, forever and completely hidden from our direct line of sight. It is this large, truly hidden portion of the Moon that constituted one of the great and most enduring mysteries of pre-space age astronomy. For thousands of years, the far side was a blank canvas, a realm of pure, scientific, and imaginative conjecture. No telescope, no matter how powerful, could bend light around the limb of the Moon to reveal its unseen hemisphere. From the first, rudimentary spyglasses of Galileo Galilei in the 17th century, which revealed the Moon to be a world of mountains and craters, to the massive, ground-based observatories of the 20th century. Every instrument was fundamentally limited by the Moon's tidally locked orientation. This lack of direct observation meant that our maps of the Moon were, by their very nature, incomplete. They represented only the visible half of a world, leaving the other side to the realm of artists' imaginings and educated, but ultimately unprovable, scientific guesses. The true and only. Reason for this prolonged mystery was the absence of a single, crucial technological leap space travel. Until the mid-20th century, the concept of sending a robotic probe, let alone a human being, beyond the Earth's atmosphere was confined to the pages of science fiction. The engineering challenges were immense, the stuff of dreams. But the dawn of the space age, sparked by the launch of Sputnik, won by the Soviet Union in 1957, fundamentally and irrevocably altered this reality. Suddenly, what was once pure fantasy became a tangible and fiercely contested national goal. But even with the advent of powerful rockets, directly observing the far side posed a unique and immediate new problem: communication. A spacecraft on the far side of the Moon would be completely and totally blocked by the 2,159-mile wide body of the Moon itself from sending its radio signals directly back to Earth. It would be in a communication blind spot, a cosmic radio shadow. Any data it collected, any images it captured, would be trapped on board, lost to us forever, unless a clever solution could be found. This challenge necessitated the development of advanced, and at the time, highly speculative, relay technologies, such as orbiting satellites that could receive a signal from a far-side probe and then retransmit it back to Earth. Without such a relay, any long-duration mission to the far side would be an exercise in futility, a journey into a silent and dataless unknown. The first, historic and successful venture to pierce this veil of mystery was undertaken by the Soviet Union. In October of 1959, their Luna 3 probe, a small, and by modern standards, incredibly primitive spacecraft, swung around the moon, becoming the first human-made object to ever capture an image of this enigmatic and long-hidden territory. The images were crude, blurry, and distorted, the product of a primitive, on-board, film processing and scanning system, and a tenuous, long-distance radio link. But they were revolutionary. They were the first flickering and ghost-like glimpses of a new world, and they revealed a landscape that was immediately and strikingly different from the familiar face of the near side. The images showed a surface that was much more heavily and uniformly cratered, and was notably and almost completely lacking in the large, dark, volcanic plains, the Maria, that so prominently defined the visible lunar landscape. This initial, stunning revelation confirmed that the far side was not simply a mirror image of the near side. It possessed its own distinct geological character, a character that hinted at a different and perhaps more ancient evolutionary history. The excitement generated by these first distant photographs was immense, and it set the stage for a new era of lunar exploration. An era in which the once hidden far side of the moon would slowly and beautifully yield its long-held secrets to the relentless and insatiable curiosity of a new and spacefaring human species. The blurry images from Luna 3 were a tantalizing first step, but they were far from providing a comprehensive understanding. NASA, then a relatively young but ambitious space agency, quickly began its own parallel program of lunar exploration, a program that would culminate in the historic human landings of the Apollo missions. While these early NASA missions, for practical reasons of landing site selection and communication, were primarily focused on the near side, the scientific imperative to explore and to understand the entire moon, including its hidden, far side, remained a powerful and enduring driving force. The journey to unveil the hidden moon was long and arduous, a journey that required decades of meticulous scientific planning, of breathtaking technological innovation, and of a fierce international competition that would ultimately push humanity beyond its terrestrial cradle and out into the vast and beautiful mystery of the cosmos. The human fascination with the moon, and with the heavens in general, is a story that is as old as our species itself. Before the advent of the scientific method, before the invention of the telescope, and long before the very concept of space travel had entered our collective imagination, the moon was a mystical and powerful object, a luminous silver orb in the night sky that inspired awe, wonder, and countless myths. Ancient civilizations across the globe wove elaborate and often beautiful tales around this celestial body, associating it with deities, with fertility, with the inexorable passage of time, and with the deep and often frightening mysteries of the night. It was seen as a silver chariot, driven by a goddess across the celestial vault, as a watchful and sometimes judgmental eye gazing down upon the affairs of mortals, or as a powerful and often capricious entity that influenced the tides, the harvests, and the very rhythms of life and death. These early pre-scientific inquiries were not about physical travel, but about finding meaning, about understanding the moon's nature and its spiritual significance in a universe that was, for the most part, a deep and terrifying unknown. But even in this age of myth, the seeds of a more scientific understanding were being sown. The ancient Greek philosopher Anaxagoras, in the 5th century before the Common Era, made the bold, and for his time, heretical suggestion that the moon was not a divine light source, but a rocky, Earth-like body, that its light was not its own, but was merely the reflected light of the sun. This was a radical and dangerous idea, one that challenged the prevailing mystical beliefs of his time, and one that laid a foundational, if rudimentary, stone for the great edifice of scientific inquiry that was to come. Aristotle, another towering figure of ancient Greek thought, built upon these early observational insights, integrating them into his comprehensive, and for centuries, dominant, geocentric model of the universe, a model in which the Earth was the fixed and special center of all creation, and all the celestial bodies, including the moon, moved in perfect, crystalline circles around it. While his model was ultimately, and spectacularly, wrong, his systematic and deeply empirical approach to observing and theorizing about the cosmos would influence Western thought for over 1,000 years. The idea of the moon as a world, a place of substance, a destination, began to take a tenuous but persistent root in these early philosophical inquiries. The dream of flight, of transcending our earthly bonds, also permeates the myths and legends of the ancient world. The story of Icarus, who fashioned wings of feathers and wax and attempted to fly to the sun, only to have his wings melt and to plunge to his death in the sea, is a powerful and enduring allegory for humanity's deep, and often tragic, aspiration to conquer the skies. While these were not direct dreams of space travel, they represented a fundamental and deeply human yearning to escape the confines of the Earth's surface, a necessary psychological precursor to the grander, and at the time, unimaginable, ambition of reaching other celestial bodies. For many centuries, the lack of a fundamental, scientific understanding of the basic principles of physics, of gravity, of the nature of the atmosphere, and the vacuum of space meant that the concept of traveling to the moon remained firmly and safely in the realm of fantasy and allegory. It was a subject for poets and storytellers, not for engineers and scientists. The 17th century, however, marked a pivotal and revolutionary shift. The invention of the telescope and its subsequent brilliant application to the heavens by Galileo Galilei fundamentally and irrevocably transformed our understanding of the universe. Galileo's telescopic observations in the early 1600s revealed that the moon was not the perfect, smooth, and ethereal sphere of Aristotelian philosophy, but a rugged and deeply familiar world, a world with mountains, with valleys, with vast dark plains, and with countless craters, a landscape that was, in many ways, strikingly similar to the landscapes of our own Earth. He even, with a beautiful and simple piece of geometric reasoning, estimated the heights of the lunar mountains by carefully observing the lengths of the shadows they cast. This new empirical evidence, derived from direct and repeatable observation, solidified the idea of the moon as a physical body, a world in its own right, a place that one could, in principle, visit. This new scientific understanding spurred a new wave of imaginative leaps, a shift from the realm of pure myth to a more grounded, albeit still fictional, exploration of the practicalities of lunar travel. In the mid-1600s, the French writer Cyrano de Bergerac, in his comical history of the states and empires of the moon, imagined a series of fantastical, but for the first time, vaguely mechanical, methods of reaching the moon, including using dew-filled bottles that would be drawn upwards by the morning sun, or a machine powered by a series of firecrackers, a primitive, but recognizable, rocket. Around the same time, the English bishop Francis Godwin, in his The Man in the Moon, described a protagonist who travels to the moon in a chariot pulled by a team of trained and exceptionally strong geese. These narratives, while charmingly unscientific, were significant. They represented a new and deeply modern human desire to imagine the mechanics of such a journey, to grapple, however imaginatively, with the practical challenges of space travel. The 19th century saw a flourishing of this new genre of speculative fiction, a genre that increasingly and skillfully intertwined the latest scientific concepts with bold, imaginative storytelling. The French novelist Jules Verne became a titan of this new form. His 1865 novel, From the Earth to the Moon, is perhaps the most famous and influential work of early space travel fiction. Verne's concept for lunar travel was a giant, spacefaring cannon, the Columbiad, which would fire a projectile containing 3 intrepid passengers directly towards the moon, while a cannon launch would, in reality, be instantly lethal to any human occupants due to the immense and crushing G-forces. Verne's attention to scientific detail was, for his time, remarkable. He consulted with scientists and engineers, and he meticulously, and for the most part, correctly, calculated the required muzzle velocity to escape the Earth's gravity, the trajectory of the projectile, and even the financial cost of such an immense undertaking. He described, with a surprising degree of accuracy, the experience of weightlessness in space and the challenges of life support in a sealed and very small capsule. His work captivated the public imagination and, in a subtle but powerful way, introduced the fundamental principles of ballistics, of orbital mechanics, and of the very possibility of space travel to a vast and hungry popular audience. Another great 19th century author, H.G. Wells, in his 1901 novel, The First Men in the Moon, conceived of a more scientifically imaginative and, in some ways, more prophetic method of propulsion, a substance he called ekpyrotic, which had the magical property of nullifying gravity. While entirely fictional, this concept allowed Wells to explore the idea of a controlled and returnable flight to the moon, and to create a vivid and often terrifying portrayal of a complex and ancient alien civilization of insect-like selenites who lived in vast underground caverns. These literary works were crucial. They were a necessary imaginative bridge between the pure fantasy of the ancient myths and the burgeoning, hard-nosed, and practical fields of physics and engineering. They cultivated a widespread public fascination with space travel, transforming it from an obscure scientific concept into an exciting and seemingly plausible future human endeavor. They inspired generations of future scientists and engineers, the very people who would one day turn these fantastical dreams into a hard and beautiful reality. The true intellectual and scientific groundwork for space travel was laid by a small and remarkable group of visionary thinkers in the late 19th and early 20th centuries. These were the true fathers of rocketry, men who, often working independently and against considerable public and scientific ridicule, developed the fundamental theoretical principles of astronautics. The first, and in many ways the most important of these, was Konstantin Tsiolkovsky, a largely self-taught and profoundly deaf Russian school teacher, working in relative and often impoverished isolation in the late 1800s and early 1900s. Tsiolkovsky, with a stunning and almost preternatural clarity, laid out the entire theoretical blueprint for space travel. He famously and correctly formulated the rocket equation, a fundamental and elegant piece of mathematics that describes the change in velocity that a rocket can achieve based on the exhaust velocity of its propellant and the ratio of its initial fueled mass to its final empty mass. This equation revealed the two crucial keys to spaceflight: high exhaust velocities and a high mass ratio. Tsiolkovsky was a passionate and early advocate for liquid-fueled rockets, recognizing their superior efficiency and controllability compared to the simple, solid-fueled rockets of his time. He was the first to seriously conceptualize multi-stage rockets. The idea of shedding the dead weight of empty fuel tanks and engines during flight, a technique that is absolutely essential for achieving orbital and escape velocities. He even, with a remarkable foresight, theorized about the use of liquid oxygen and liquid hydrogen as propellants, a combination that, due to its exceptional energy density, is still used in many of our most powerful modern rockets today. But Tsiolkovsky was more than just a brilliant technical theorist. He was a deep, and in some ways, mystical, philosophical thinker. He envisioned a future for humanity that lay not on Earth, but in space. He dreamed of space stations, of lunar bases, of the colonization of the solar system, and of an ultimate human destiny among the stars. His work, though largely unknown outside of Russia during his lifetime, provided the complete and uncannily accurate theoretical foundation upon which all subsequent practical developments in rocketry would be built. Across the Atlantic, in the United States, another, and very different, kind of pioneer was at work. Robert Goddard, an American physicist, was not primarily a theorist, but a tireless, and often frustrated, hands-on experimenter. He was often ridiculed by the press, who famously and wrongly asserted in a New York Times editorial that a rocket could not work in the vacuum of space because it would have nothing to push against. But Goddard, undeterred, persisted, and in 1926, on a cold March day in a field in Auburn, Massachusetts, he achieved a monumental and historic feat, the launch of the world's first liquid-fueled rocket. The rocket, which he had nicknamed Nell, was a small and rather unimpressive-looking contraption. It flew for only 2.5 seconds and reached an altitude of only 41 feet, but it was a transformative moment. It was the Kitty Hawk of rocketry, the first tangible proof that the theoretical promise of liquid-fueled rockets could be turned into a working physical reality. Goddard continued to develop and test more powerful and sophisticated rockets throughout his career, often facing funding challenges and working with very limited resources. He was a prolific inventor, and he held patents for many of the key components of a modern rocket, including multi-stage designs, fuel pumps, and gyroscopic guidance systems. He was the man who solved, through painstaking and often dangerous trial and error, many of the practical engineering problems that Tsiolkovsky had only dreamed about. And in Germany, another key figure, Hermann Oberth, was independently exploring the theoretical possibilities of spaceflight. His 1923 book, The Rocket into Interplanetary Space, was a rigorous mathematical exploration of the principles of rocket propulsion, and it had a profound influence on a generation of German rocket enthusiasts, including a young and ambitious engineer named Wernher von Braun. Together, Tsiolkovsky, Goddard, and Oberth are rightly known as the fathers of modern rocketry. Their independent, but remarkably convergent work formed the solid theoretical and practical bedrock of astronautics. They were the ones who showed that escape velocity, the speed required to break free from a planet's gravitational pull, was not an impossible dream, but a solvable, if difficult, engineering challenge. The grim and terrible reality of the Second World War inadvertently and tragically accelerated this development. The German V-2 rocket, developed under the leadership of Wernher von Braun, was a weapon of terror, but it was also the world's first large-scale, liquid-fueled, ballistic missile, a machine that was capable of reaching the very edge of space. After the war, both the United States and the Soviet Union scrambled to capture the German rocket scientists and their advanced V-2 technology, a process that provided a significant and morally complex leap forward for their own nascent missile and space programs. The dawn of the Cold War, in the mid-20th century, then provided the final, powerful geopolitical impetus for the race to space. The launch of Sputnik, won by the Soviet Union in October of 1957, was a profound, and for many in the West, terrifying, shock. It was a clear and unambiguous demonstration of Soviet technological prowess, and it ignited a fierce and desperate determination in the United States to catch up and to surpass their ideological rivals. This event led directly to the creation of the National Aeronautics and Space Administration, NASA, in 1958, a new civilian agency that would consolidate and lead America's efforts in space. The race to the moon was on, and the once fantastical dreams of the early visionary thinkers were about to become a monumental national endeavor, an endeavor that would, in the short span of a single decade, take humanity from its first tentative steps into orbit to its first giant leap onto the surface of another world. For untold millennia, the far side of the moon remained an impenetrable mystery to humanity. From our terrestrial vantage point, only one familiar face of our celestial neighbor was ever visible, a beautiful and frustrating consequence of the gravitational dance known as tidal locking. This meant that any true knowledge of the moon's other hidden hemisphere would require a monumental leap in our technological capabilities, a leap that would take us beyond the Earth's atmosphere and into the vast, dark expanse of cislunar space. The mid-20th century witnessed the beginning of this transformative era, as the burgeoning space race between the United States and the Soviet Union propelled humanity towards its first direct observations of this enigmatic lunar territory. And it was the Soviet Union, with its early and impressive lead in powerful long-range rocket technology, that would achieve this pioneering feat, providing the world with its first blurry, but profoundly significant, glimpses of the moon's unseen side. The mission that was responsible for this groundbreaking achievement was Luna 3, a small, and by today's standards, incredibly primitive robotic probe. Its launch, in October of 1959, came just 2 years after the momentous, and for the West, deeply shocking, launch of Sputnik 1, the world's first artificial satellite. The Luna 3 mission was audacious for its time. It was designed not just to orbit the Earth, but to journey 250,000 miles to the moon, to swing around it in a complex gravitational ballet, and then, if all went well, to transmit its precious photographic cargo back across the vast and empty gulf of space. Its primary objective was singular, historic, and revolutionary: to photograph the side of the moon that had never before been seen by a human eye, or indeed, by any terrestrial instrument. The design of the Luna 3 spacecraft was a marvel of late 1950s engineering, a testament to the ingenuity of the Soviet space program, but also a reflection of the severe technological constraints of the era. It was a cylindrical craft, equipped with solar panels for power and a set of simple, whip-like antennas for communication. Its most crucial and most ingenious component was its imaging system. This was not a digital camera, which had not yet been invented. It was a complex and delicate system of 2 film-based cameras, a small onboard automated film processing laboratory, and a miniature television-like scanning device. The system was designed to capture a series of images on traditional photographic film. Then, in the harsh and unforgiving vacuum of space, the film would be automatically developed, fixed, and dried. Once the images were processed, a tiny flying light spot would scan the developed film, line by line, converting the variations in light and shadow into an analog, electrical signal. This signal was then transmitted, slowly and painstakingly, back to the massive radio dishes of the deep space network on Earth. This method was inherently prone to noise, to distortion, to the 1,001 things that can go wrong in a complex, automated system operating hundreds of thousands of miles from home. But it was the cutting edge of remote imaging technology for its time. The trajectory of Luna 3 was another masterpiece of early celestial navigation. It was not designed to enter a stable orbit around the Moon, but to perform a circumlunar flyby. It was launched from Earth on a direct translunar trajectory. It then used the Moon's own gravity to bend its path, to swing it around the far side, and then to fling it back towards the Earth on a long, looping, and highly elliptical orbit. This gravity assist maneuver was a clever and efficient way to achieve the desired path without the need for a large and heavy onboard rocket engine for course correction. The timing of the photographic sequence was critical. The spacecraft had to be in the right place at the right time, with the sun in the right position to illuminate the far side. On October 7th, 1959, as Luna 3 gracefully arced around the far side of the Moon, its cameras clicked and whirred, capturing 29 images of the previously unseen hemisphere. The images, once they were finally received and processed on Earth, were, by modern standards, of a shockingly poor quality. They were blurry. They were low resolution. They were streaked with static and marred by transmission artifacts. But they were, without a doubt, one of the most important and most breathtaking set of images ever taken. They were the first empirical evidence of what lay on the other side of our own Moon. And what they revealed was a landscape that was immediately and strikingly different. The familiar near side of the Moon is defined by its extensive, dark, and relatively smooth plains, the Maria. But the Luna 3 images showed a far side that was almost completely devoid of these large, dark features. Instead, it was a continuous and seemingly endless expanse of bright, rugged, and heavily cratered terrain. This was not just a minor cosmetic difference. It was a profound geological dichotomy. It suggested that the two hemispheres of the Moon had experienced vastly different evolutionary histories. The far side appeared to be an older, more ancient, and more heavily battered surface, a surface that had not been subject to the same large-scale volcanic resurfacing that had shaped the near side. This single, stunning observation sparked a revolution in lunar science. It forced a complete re-evaluation of our models of the Moon's formation, of its internal structure, and of its thermal history. The simple and long-held assumption of a uniform, symmetric Moon was shattered forever. The naming of the newly discovered features on the far side also began with these first blurry images. The Soviet scientists, in a move that reflected the national pride of their achievement, named one of the few, small, dark patches they could discern Mare Moscoviense, the Sea of Moscow. A prominent crater was named after their great visionary rocket pioneer, Konstantin Tsiolkovsky. These names were the first human brushstrokes on a canvas that had been, for all of history, completely blank. The impact of Luna 3's achievement was immense. It was a massive propaganda victory for the Soviet Union in the intense, and often bitter, Cold War space race. It was a moment of deep and almost universal awe for the public around the world, a moment that transformed the Moon from a distant, mystical object into a real, tangible, and now partially known world. And for the scientific community, it was a tantalizing and deeply provocative first glimpse into a new and unknown land, a glimpse that would ignite a decades-long and still ongoing quest to fully understand the profound and beautiful asymmetry of our own celestial companion, Celestial. The launch of Sputnik 1 in 1957 was a profound, and for many in the United States, a deeply unsettling wake-up call. The small, beeping satellite, circling the Earth every 96 minutes, was a clear and unambiguous demonstration of Soviet technological prowess, and it ignited a fierce, and often frantic, sense of urgency in the American government and public. Before Sputnik, American efforts in space were fragmented. a patchwork of competing and often uncoordinated programs within the different branches of the military, and a smaller civilian research effort led by the National Advisory Committee for Aeronautics, or NACA. The Sputnik crisis made it abundantly and painfully clear that a new, more unified, and more ambitious approach was needed. In July of 1958, President Dwight D. Eisenhower signed the National Aeronautics and Space Act into law, creating a new, powerful, and civilian-led agency, NASA. The new agency absorbed the old NACA, along with its skilled engineers and its world-class research facilities, and it was given a clear and audacious mandate to lead America's efforts in the peaceful exploration of space. The initial goal was simply to catch up to the Soviets, but this soon evolved into a much grander and more ambitious vision, a vision that would be articulated with a powerful and enduring rhetoric by a new, young president. In 1961, President John F. Kennedy, in a speech before a joint session of Congress, threw down the ultimate cosmic gauntlet. He challenged the nation to commit itself to achieving the goal, before the decade was out, of landing a man on the moon and returning him safely to the Earth. This was not just a scientific goal, it was a political and deeply symbolic one. It was a declaration of national will, a bold and risky gambit in the high-stakes, ideological battle of the Cold War. And it was a challenge that would galvanize the nation and set NASA on a course that would lead to one of the greatest and most inspiring adventures in all of human history. But before humans could take their first giant leap, a vast amount of groundwork had to be laid. The moon was still, in many ways, an unknown and dangerous world. We needed to know what its surface was like, whether it was solid enough to support a lander, what dangers it might hold. And so, before the Apollo astronauts could fly, their robotic scouts had to go first. The Ranger program was NASA's first, and often frustrating, attempt to get a close-up look at the lunar surface. The plan was simple, if brutal, to send a series of probes on a direct collision course with the moon, transmitting high-resolution television images back to Earth in the final, frantic minutes before their impact. The early Ranger missions were a string of heartbreaking failures, a testament to the immense, and often unforgiving, difficulty of early, deep space exploration. But with Ranger 7, in July of 1964, NASA finally succeeded. The probe transmitted over 4,300 close-up images, revealing the lunar terrain in unprecedented detail, and confirming that the surface was, indeed, solid enough to land on. Following the success of the Ranger impactors, NASA embarked on the much more complex and much more ambitious Surveyor program. The goal of Surveyor was not to crash, but to land, to achieve the first, controlled, soft landing on the lunar surface. Each Surveyor spacecraft was a marvel of 1960s engineering, an insect-like contraption equipped with a powerful, solid-fuel retro rocket to slow its descent, and a set of smaller, liquid-fueled Vernier engines for fine-tuned terminal guidance. In June of 1966, Surveyor 1 made a perfect, gentle touchdown on the ocean of storms, a stunning and deeply emotional success for the young space agency. It transmitted over 11,000 images of its surroundings, showing a landscape of fine-grained, sandy material littered with small rocks and pebbles. Later, Surveyor missions carried more sophisticated instruments, including a robotic arm with a scoop that could dig into the lunar soil, and an alpha scattering device that could perform a direct chemical analysis of the lunar regolith. The Surveyor program was the ultimate and successful dress rehearsal for the Apollo landings. It proved that we could land safely, and it gave us our first direct and tangible knowledge of the strange, new ground upon which our astronauts would one day walk. At the same time, the Lunar Orbiter program was systematically mapping the entire moon from orbit, including both the near and the far sides, with a series of 5 highly successful photographic missions. The primary goal was to scout and to certify the safest and most scientifically interesting potential landing sites for the Apollo missions. The orbiters produced a comprehensive and beautiful photographic atlas of the moon, a set of images that not only served a crucial practical purpose, but also revealed, in stunning, high-resolution detail, the full, rugged, and ancient beauty of the lunar landscape, together the Ranger Surveyor. And lunar orbiter programs were the necessary, robotic precursors to the human adventure that was to come. They were the eyes, the ears, and the hands that we sent ahead, the silent and often heroic scouts that paved the way for the first human steps onto another world. The Apollo program was not just a technological achievement. It was a human drama of immense proportions, a story of courage, of ingenuity, of sacrifice, and of profound, and often unexpected, discovery. And it was the astronauts of the Apollo missions who would become the first, and so far, only, human beings to ever see, with their own eyes, the hidden, far side of the moon. The first of these historic journeys was Apollo 8, in December of 1968. In a bold, and at the time, deeply risky decision, NASA sent the crew of Frank Borman, James Lovell, and William Anders on a direct circumlunar flight, the first time that human beings had ever left the gravitational embrace of the Earth and traveled to another celestial body. As their spacecraft rounded the limb of the moon, and the Earth, for the first time in human history, disappeared from view, they were greeted by a landscape that was both awe-inspiring and deeply unsettling. "It's a vast, lonely, forbidding expanse of nothing," one of the astronauts reported back to a transfixed world. "It looks like plaster of Paris." Their live television broadcasts, though grainy and in black and white, gave humanity its first shared human experience of another world. And it was on this mission, as they came around from the far side for the 4th time, that William Anders took one of the most iconic and most influential photographs in all of human history, Earthrise. The image of our own small, fragile, and beautiful blue planet rising above the stark, gray, and lifeless horizon of the moon was a profound, and for many, a deeply spiritual moment. It was a picture that, in a single, silent frame, captured the beauty of our own world, the desolation of the moon, and the profound and inescapable truth of our own cosmic isolation. The missions that followed, from Apollo 10's full dress rehearsal to Apollo 17's final triumphant landing, all involved multiple orbits around the moon. And with each orbit, the astronauts were given a new, and often different, view of the far side. The command module pilots, who remained in orbit while their crewmates descended to the surface, Michael Collins on Apollo 11, Richard Gordon on Apollo 12, Stuart Roosa on Apollo 14, Al Worden on Apollo 15, Ken Mattingly on Apollo 16, and Ron Evans on Apollo 17 all experienced a unique and profound form of solitude. For long periods of time, they were the most isolated human beings in the history of the universe, alone in their tiny spacecraft, circling a dead world, their only connection to the 7 billion other souls of their species. A fragile radio link that was, for 20 minutes of every 2-hour orbit, completely and totally silent. As they passed behind the moon into the radio shadow, they were truly and completely on their own. And in these moments of profound, and beautiful isolation. They were the only human beings to ever see the full sunlit expanse of the far side. Their descriptions, in their mission logs and their later memoirs, are a testament to the power and the poetry of human exploration. They spoke of its stark and almost brutal beauty, of its endless and seemingly uniform sea of craters, of its profound and almost terrifying sense of ancientness. It was a world that had not been softened by the gentle hand of erosion, a world that wore the scars of its violent 4-billion-year-long history on its face. It was a world, they all agreed, that was not like home. Even the ill-fated Apollo 13 mission, a mission that was a near disaster, provided a dramatic and unintentional human encounter with the far side. After an explosion crippled their spacecraft on the way to the moon, the crew was forced to use the moon's gravity to swing them around on a free return trajectory back to Earth. For the distressed crew of James Lovell, Jack Swigert, and Fred Hayes, the long, silent pass behind the far side was a moment of immense and almost unbearable tension, a period of radio silence when they were at their most vulnerable, their most isolated, and their most uncertain of their own survival. Their experience, though not one of scientific observation, was a powerful and deeply human testament to the isolating and unforgiving nature of this hidden lunar hemisphere. The cumulative human observations from all the Apollo missions, when combined with the precise and systematic data from the robotic probes, gave us a new and much richer understanding of the moon. They confirmed, in a direct and visceral way, the profound geological asymmetry between the two hemispheres. And they gave us a new and more profound sense of our own small and precious place in the vast and often hostile cosmos. The surface of the moon is a museum of cosmic violence, a gallery of scars that tells the long and tumultuous story of the early solar system. And the largest, oldest, and most magnificent exhibit in this museum is the South Pole Aitken Basin, a colossal impact structure on the lunar far side that is one of the largest and oldest known impact features in our entire solar system. The basin was not discovered in a single eureka moment, but was gradually and painstakingly revealed through a series of robotic missions that have, over the decades, peeled back the layers of its mystery. The first, faint hints of its existence came from the blurry 1959 images from the Soviet Luna 3 probe. But it was NASA's Lunar Orbiter and Apollo missions in the 1960s that provided the first high-resolution photographic evidence of the vast and subtle depression that marks its location. And it has been the more recent and more sophisticated missions of the late 20th and early 21st centuries that have truly brought this ancient and monumental feature into sharp focus. The basin gets its name from its location. It is centered near the lunar South Pole, and its northern rim is marked by the smaller, but still prominent, Aitken crater. Its dimensions are staggering. It is approximately 2,500 kilometers, or 1,550 miles, in diameter, a distance that would stretch from New York City to Dallas. And it is incredibly deep, ranging from 8 to 13 kilometers, or 5 to 8 miles, from its highest mountainous rim to its lowest cratered floor. It is an impact scar of truly planetary proportions, and it is ancient. Scientists estimate that the impact that created the South Pole Aitken Basin, or SPA, occurred very early in the Moon's history, sometime between 4.3 and 4.2 billion years ago. This places its formation squarely within the late heavy bombardment, a hypothesized and still not fully understood period in the early solar system when the inner planets and their moons were subjected to an intense and prolonged fusillade of asteroids and comets. The SPA basin is, in a sense, the moon's oldest and deepest wound. The impact that created it must have been an event of almost unimaginable violence. The prevailing theory is that it was formed by the collision of a massive asteroid or comet, perhaps several hundred kilometers in diameter, traveling at a speed of tens of thousands of miles per hour. The energy released in this cataclysmic event would have been far, far greater than all of the nuclear weapons on Earth combined. It would have instantaneously vaporized, melted, and ejected a colossal amount of the moon's primordial crust, sending a shockwave of seismic energy reverberating through the entire lunar body, the most profound and scientifically significant. Consequence of this impact is that it is thought to have punched a hole, clear through the moon's crust, and to have excavated material from the deep underlying mantle. This is a discovery of immense importance, as it offers us a rare and precious natural window into the deep interior of the moon. NASA's missions have been paramount in confirming this mantle excavation hypothesis. In the 1990s, the Galileo and Clementine spacecraft, with their multispectral imagers, provided the first tantalizing hints that the floor of the SPA basin had a different and unusual mineral composition. Then, in 1998, the Lunar Prospector mission, with its gamma-ray spectrometer, created the first global maps of the moon's elemental composition. These maps revealed a striking anomaly. The floor of the SPA basin has a significantly higher concentration of iron and titanium than the surrounding highland crust. These are elements that are thought to be more abundant in the denser mantle material, but the most comprehensive and most definitive. Data has come from the Lunar Reconnaissance Orbiter, or LRO, which has been orbiting the moon since 2009. LRO's suite of advanced instruments has given us an unprecedented and multifaceted view of the SPA basin. Its laser altimeter has created a precise, three-dimensional topographic map, revealing the basin's true depth and its complex, multi-ring structure. Its radiometer has mapped the thermal properties of the surface, providing further clues to its mineral composition. And its high-resolution cameras have given us stunning, detailed images of the terrain within the basin. When all of this data is combined, a clear and consistent picture emerges. The floor of the South Pole Aitken Basin is a unique geological province, a place where the deep and normally hidden interior of the moon has been brought up to the surface. It is a natural laboratory for studying the composition of the lunar mantle, a study that is crucial for understanding the moon's overall formation, its thermal history, and its differentiation into a layered planetary body. This is a gift of almost incalculable scientific value. It gives us a way to sample the deep interior of another world without the immense, and at present, impossible, technological challenge of having to drill tens of kilometers through its solid, rocky crust. The SPA Basin is also a place of great interest for future exploration. It encompasses the lunar South Pole, a region where, in the deep and permanent shadows of certain craters, LRO and other missions have confirmed the existence of significant deposits of water ice. This discovery has transformed our view of the moon from a bone-dry, barren world into a place with a potentially valuable and life-sustaining resource. This water ice, if it can be mined and processed, could provide drinking water, breathable oxygen, and rocket propellant for future human lunar outposts. The South Pole Aitken Basin, with its unique, ancient geology, its window into the lunar mantle, and its proximity to these precious polar ice deposits, is, without a doubt, one of the most scientifically compelling and strategically important locations in our entire solar system. It is a place where the deep past and the potential future of lunar exploration come together in a single, magnificent, and awe-inspiring landscape. And in 2019, humanity, through the Chinese Chang'e 4 mission, took its first, historic, robotic step into this new and exciting world. A world that was, for so long, hidden from our view. The surface of the moon is a history book written in the language of craters, unlike the Earth, with its dynamic atmosphere, its flowing water, and its active plate tectonic geology. The moon is a world of profound and beautiful stasis. It has no wind, no rain, no rivers to erode its surface. Its geological engine cooled and died billions of years ago. And so, the scars of its violent past, the countless impact craters that have pockmarked its surface over the eons, have been preserved with an almost perfect and often breathtaking clarity. But this history book is not a uniform one of the most striking and most fundamental discoveries of the space age has been the profound and deeply mysterious asymmetry between the moon's near side and its far side. The near side, the face that is forever turned towards the Earth, is a world of two distinct terrains, the bright, ancient, and heavily cratered highlands, and the dark, younger, and relatively smooth Maria. The far side, on the other hand, is an almost continuous and seemingly endless expanse of heavily cratered highlands, the great dark Maria. The seas of solidified lava that so prominently define the near side are almost completely absent. This stark dichotomy in the density of craters and in the extent of volcanic resurfacing is one of the central puzzles of lunar science and NASA's missions. From the first, robotic scouts to the human explorers of the Apollo program have been instrumental in piecing together the clues that are now allowing us to solve it. The answer to this puzzle lies deep within the moon's own hidden interior. The key is the thickness of the lunar crust. Our detailed global maps of the moon's gravity field, most notably from the Grail mission, have revealed that the crust on the far side is significantly and systematically thicker than the crust on the near side. On average, the far side crust is about 60 kilometers thick, while the near side crust is only about 30 kilometers thick. This is a profound and fundamental asymmetry, and it is thought to be a relic of the moon's very formation. In the aftermath of the giant impact that created the moon, as the debris coalesced and the moon cooled from a molten state, the Earth's immense gravitational pull and the uneven distribution of heat-producing radioactive elements may have led to this lopsided crustal structure. And this difference in crustal thickness has had a dramatic and lasting impact on the moon's geological evolution. The Maria were formed by vast outpourings of basaltic lava from the moon's deep, and at the time, still molten, mantle. On the near side, the thinner crust provided an easier path for this magma to reach the surface. The immense impacts that created the great near-side basins also created deep fractures in this thinner crust, providing ready-made conduits for the upwelling lava. The result was a series of massive volcanic flood events that filled these basins and buried the older, cratered terrain beneath them. On the far side, however, the much thicker crust acted as a formidable barrier. Even when giant impacts created vast basins, the magma from the mantle simply could not, for the most part, find its way to the surface. The far side, therefore, was largely spared from this volcanic resurfacing. Its ancient cratered highlands, the primordial crust of the moon, were preserved. It is a more pristine, and in many ways, a more honest record of the early violent history of the solar system. This story is further supported by another, subtle, but crucial, discovery. The Lunar Prospector mission, with its gamma-ray spectrometer, found that the heat-producing radioactive elements of potassium, uranium, and thorium are not uniformly distributed throughout the moon. They are concentrated in a vast geological province on the near side, a region known as the Procellarum Creep Terrain. This region, with its higher concentration of internal heat sources, would have remained hotter and more volcanically active for longer, further contributing to the extensive mare-forming volcanism on the near side. The far side, being relatively depleted in these elements, would have cooled more quickly. its volcanic engine sputtering and dying out much earlier in its history. The implications of this cratered asymmetry are profound. It means that the far side of the moon is, in a very real sense, a different world. It is an older world, a more ancient world, a world that has preserved a more complete and more pristine record of the late heavy bombardment. That intense and chaotic period in the early solar system when the inner planets were subjected to a relentless fusillade of asteroids and comets. By studying the number, the size, and the distribution of the craters on the far side, and by comparing them with the ages of the rocks brought back by the Apollo astronauts from the near side, we can reconstruct the history of this bombardment with a remarkable degree of precision. This is a technique known as crater counting, and the moon, with its two distinct and beautifully preserved faces, is our primary and most valuable Rosetta Stone for deciphering the ancient and violent history of our entire solar system. The far side is not just the other side of the moon, it is a window into the deep past, a silent and beautiful testament to the fiery and creative chaos of our own cosmic origins. The lunar highlands, the bright, rugged, and ancient terrains that dominate the far side of the moon, are the oldest and in many ways the most important landscapes on our celestial neighbor. They are the primordial crust of the moon, a fossilized record of its fiery birth and its turbulent youth. And they hold the key to understanding not just the history of the moon, but the very process of planetary formation itself. The prevailing theory for the origin of the highlands is the lunar magma ocean hypothesis. This theory proposes that shortly after its formation, some 4.5 billion years ago, the moon was a global, molten sphere, a vast, incandescent ocean of rock. As this magma ocean slowly cooled and solidified, a process of differentiation occurred. Denser minerals, rich in iron and magnesium, crystallized and sank towards the center, forming the moon's mantle and its small metallic core. Lighter minerals, however, particularly a type of feldspar known as plagioclase, crystallized and floated to the surface like a layer of creamy slag on a molten metal. Over millions of years, this buoyant, plagioclase-rich material accumulated and solidified to form a thick, global crust of a light-colored, low-density rock called anorthosite. This primordial, anorthositic crust is what we now see as the lunar highlands. This theory, which was first proposed in the 1970s, was a bold and brilliant piece of scientific inference, and it has been confirmed with a stunning degree of precision by the samples brought back from the moon by the Apollo astronauts. The rocks collected from the highland regions on the near side were, indeed, predominantly anorthosites, their great age confirming their primordial origin. The highlands are a landscape of almost unimaginable antiquity, a surface that has been preserved, largely unchanged, for over 4 billion years. And they are a landscape of almost unimaginable violence. They are saturated with impact craters, the result of a relentless and seemingly endless bombardment by asteroids and comets in the early, chaotic history of the solar system. The surface of the highlands is not made of pristine, solid bedrock. It is a deep and thoroughly pulverized layer of regolith, a mixture of fine dust, broken rock fragments, and small, glassy beads that have been formed by the immense heat and pressure of countless impacts. And beneath this regolith lies a thick layer of breccia, a type of rock that is itself composed of the angular, cemented together fragments of older, shattered rocks. The highlands are a landscape that has been broken and rebroken again, a testament to a history of violence that is almost beyond our comprehension. And yet, it is precisely this violent history that makes the highlands so scientifically valuable. They are a pristine and beautifully preserved record of the late heavy bombardment. By studying the craters of the highlands, we can learn about the size, the number, and the nature of the objects that were careening through the early solar system. This is information that is crucial for understanding how the planets themselves formed, and how our own home world, the Earth, survived this early and very dangerous period of its life. The Earth, too, must have been subjected to this same intense bombardment, but on our dynamic and geologically active planet. The evidence of this ancient history has been almost completely erased, wiped clean by the relentless processes of plate tectonics, of volcanism, of erosion. The moon, in its beautiful and silent stasis, has preserved the story that the Earth has forgotten. It is our celestial attic, our planetary memory, a place where the deep and often violent secrets of our own cosmic family are stored, the persistent and deeply ingrained. Popular misconception of a dark side of the moon is a beautiful example of how a simple linguistic ambiguity can lead to a profound and enduring scientific misunderstanding. The term dark side has a powerful and almost mystical resonance. It conjures up images of a perpetually shadowed and mysterious hemisphere, a realm of eternal night. But the reality is far more mundane, and in many ways, far more interesting. The moon does not have a dark side, it has a far side. And the far side is not perpetually dark. It experiences a regular and predictable cycle of day and night, just like the near side, and just like our own Earth. The confusion arises from the phenomenon of tidal locking, because the moon's rotation is synchronized with its orbit. The same hemisphere, the near side, is always facing the Earth. The other hemisphere, the far side, is therefore always facing away from us. It is dark in the old-fashioned sense of being unknown, of being hidden from our view. But it is not dark in the sense of being unlit. The source of light in our solar system is the sun, not the Earth. And as the moon orbits the Earth, it is also, of course, orbiting the sun over the course of a single lunar day. A period of about 29.5 Earth days, the sun's light sweeps across the entire spherical surface of the moon. Every part of the moon, both the near side and the far side, experiences about 2 weeks of continuous, brilliant daylight, followed by 2 weeks of deep, cold, and continuous night. The phases of the moon, as seen from Earth, are a direct consequence of this changing illumination. When we see a new moon, the moon is positioned between the Earth and the sun. The side of the moon that is facing us, the near side, is in darkness. But at that very same moment, the far side of the moon is fully illuminated, basking in the light of its own high noon. Conversely, when we see a full moon, the Earth is positioned between the sun and the moon. The near side is fully illuminated, and at that moment, the far side is in the midst of its long, 2-week-long night. The first, definitive, and human confirmation of this simple but profound astronomical fact came with the Apollo 8 mission in December of 1968. As the astronauts became the first human beings to ever orbit the moon, their television camera, broadcasting back to a transfixed world, showed them the sunlit and deeply cratered landscape of the far side, and the iconic Earthrise photograph, taken on that same mission, is a beautiful and powerful testament to this reality. The image shows our own blue and white planet, rising above a stark, gray, and clearly sun-drenched lunar horizon. The landscape in the foreground of that photograph is on the far side of the moon. The only places on the moon that are truly perpetually dark are the deep and frigid floors of certain craters at the lunar poles, because of the moon's very small axial tilt. The sun is always very low on the horizon at the poles. This means that the floors of some deep craters are forever shielded from the direct rays of the sun. These permanently shadowed regions are some of the coldest places in our entire solar system. And it is in these cold, dark traps that the moon has been hiding its most precious and most surprising secret. For most of the 20th century, the scientific consensus was that the moon was a bone-dry and completely waterless world. The rock samples brought back by the Apollo astronauts, when first analyzed, seemed to confirm this view. They were found to be almost completely devoid of water. This dry moon paradigm had a profound and chilling effect on our plans for future human exploration. It meant that any long-term human presence on the moon would be an immense and costly logistical challenge, requiring all the necessary water for drinking, for life support, and for growing food to be ferried, at great expense, from the deep gravitational well of the Earth. But in the last few decades, this paradigm has been completely and beautifully overturned. A series of sophisticated robotic missions, many of them led by NASA, has revealed that the moon is not as dry as we once thought. In the deep, dark, and permanently shadowed craters at its poles, it is hoarding a vast and potentially invaluable reservoir of water ice. The first tantalizing hints came in the 1990s from the Clementine and Lunar Prospector missions. These orbital probes, using radar and a neutron spectrometer, detected the telltale signatures of hydrogen concentrated in the polar regions. The most plausible form for this hydrogen, in these incredibly cold, permanently shadowed environments, was water ice. But the definitive, smoking gun proof came in 2009 with NASA's spectacular and deliberately destructive LCROSS mission. The mission involved intentionally crashing a spent Centaur rocket stage into a permanently shadowed crater at the moon's south pole. A second shepherding spacecraft then flew through the plume of debris that was kicked up by the impact, analyzing its composition with a suite of onboard instruments. The data was unambiguous. The spectrometers on the shepherding spacecraft detected the clear and unmistakable spectral signatures of both water vapor and water ice. The water was real. The discovery of water on the moon is a true game changer. Water is the single most important resource for supporting a long-term human presence in space. It can be used for drinking and for growing food. It can be split through electrolysis into its constituent elements, hydrogen and oxygen. The oxygen can be used for breathable air, and the hydrogen and oxygen, when recombined, are a powerful and clean rocket propellant. The moon, it turns out, has its own built-in gas station, the ability to mine and to utilize this lunar water. A process known as in situ resource utilization, or ISRU, is the key to creating a sustainable and ultimately a self-sufficient human presence on the moon. It is the key to breaking our complete and costly reliance on the Earth for all of our resources. It is the key that will unlock the door to a future where the moon is not just a place we visit, but a place where we live, and a place from which we can journey onwards to Mars and beyond. The discovery of water on the moon has transformed our nearest celestial neighbor from a barren geological museum into a dynamic and strategically important new frontier. A frontier that is rich with both scientific mystery and profound human possibility. The moon's gravitational field is not the smooth, uniformed, and perfectly spherical field of a textbook problem. It is a lumpy and complex gravitational landscape, a landscape of subtle hills and valleys that is a direct reflection of the uneven distribution of mass within the moon's interior. These gravity anomalies were first discovered serendipitously in the 1960s, when the mission controllers for NASA's Lunar Orbiter and Apollo missions noticed that their spacecraft were being mysteriously and frustratingly tugged off course as they orbited the moon. These unexpected orbital perturbations were caused by localized regions of unusually strong gravitational pull, regions that were quickly and evocatively dubbed mascons, for mass concentrations. The most prominent of these mascons were found to be associated with the large, circular, mare basins on the near side. This was a deep, and at the time, completely unexpected puzzle. These basins are the lowest points on the lunar surface. Why should they be the location of a large, excess mass? The answer, we now know, lies in a combination of two effects. The immense impacts that created these basins not only excavated a huge amount of the low-density crustal material, but they also caused the denser underlying mantle material to rebound upwards closer to the surface. And then, these thinned-out basins were filled with a thick and very dense layer of basaltic lava. It is this combination of a raised, dense mantle and a thick, dense lava fill that creates the strong, positive gravity anomaly of the mascons. The fact that these mascons are still there, that they have not been erased by the slow, isostatic adjustment of the lunar crust over billions of years, tells us something profound about the moon's interior. It tells us that the moon's outer, solid layer, its lithosphere, has been very thick and very rigid for a very long time. It cooled and solidified much more quickly than the Earth's, and it has been for most of its history, a geologically dead and unyielding world. The far side, with its almost complete lack of large maria, also, unsurprisingly, lacks these large, prominent mascons. Even the colossal South Pole Aitken Basin does not have a strong, positive mascon. Its gravity signature is more subtle and more complex, a reflection of its different and more ancient history. But the most detailed and most beautiful map of the moon's gravity field has come from NASA's Grail mission. In 2011, two identical spacecraft, named, charmingly, Ebb and Flow, were placed in a close, tandem orbit around the moon by precisely and continuously measuring the tiny changes in the distance between the two spacecraft as they orbited, to an accuracy of a few microns. The mission was able to create an incredibly high-resolution map of the entire lunar gravity field. The map is a work of scientific art. It reveals not just the large mascons, but a wealth of smaller and more subtle anomalies associated with individual craters, with buried volcanic structures, and with the deep tectonic faults of the lunar crust. It is a new and powerful way of seeing the moon, an X-ray vision that allows us to peer beneath the surface and to map the hidden and complex architecture of its interior. The moon today does not have a global magnetic field. It lacks the hot convecting and electrically conducting liquid outer core that is required to generate a planetary dynamo, the kind that creates the Earth's protective magnetosphere. And yet, the moon is not entirely non-magnetic. The rock samples brought back by the Apollo astronauts were found to be surprisingly and mysteriously magnetic. And our orbital probes have detected a series of weak, localized, and patchy magnetic anomalies embedded in the lunar crust. These are fossil magnetic fields, the frozen and ghostly remnants of a time long ago when the moon was a very different and much more dynamic world. The existence of these remnant magnetic fields is a profound and beautiful clue. It tells us that in its distant past, for a period of at least 1 billion years, the moon did have a global magnetic field. It did have a hot, molten, and convecting core. It did have a dynamo. This discovery has revolutionized our understanding of the moon's thermal history, showing us that it was not a simple, cold, and inert body, but a true, and for a time, a geologically active planet. The distribution of these fossil magnetic fields is also deeply strange. They are much stronger and much more prevalent on the far side of the moon than on the near side. And some of the strongest of these far-side anomalies are found in a very peculiar and very specific location at the antipode, the point on the moon's surface that is diametrically opposite to the large, young, and near-side impact basins, like Mare Imbrium. This is a stunning and deeply suggestive correlation, and it has led to a beautiful and compelling theory. The idea is that the immense energetic impacts the UAT created these near-side basins sent a powerful and highly focused seismic shockwave reverberating through the entire, and at the time, still molten, body of the moon. When this shockwave converged at the antipode, on the far side, it created a region of intense, localized heating, and perhaps even melting of the crustal rock. As this rock then cooled and solidified, in the presence of the moon's ancient global magnetic field, it became strongly and permanently magnetized. The impact, in a sense, acted as a cosmic recording head, imprinting the signature of the global magnetic field onto the crustal rock at its antipode. And these ancient magnetic memories are not the only strange and beautiful feature of the lunar surface. There are also the lunar swirls, strange, sinuous, and bright patterns that are found in several locations on the moon. These swirls are not associated with any topographic features. They are like delicate and ghostly paintings on the lunar regolith. And they are almost always found in regions of strong, localized magnetic anomalies. The leading theory is that these magnetic anomalies are acting as miniature and very weak magnetospheres, shielding the surface from the constant, darkening effect of the solar wind, and thus preserving the brighter, more pristine appearance of the underlying soil. The lunar swirls are a direct and beautiful visual manifestation of the moon's hidden and fossilized magnetic past, the story of the moon. As revealed by our decades-long and still ongoing scientific exploration, is a story of profound and beautiful asymmetry. It is a tale of two very different worlds bound together in a single celestial body. The near side is a world of dramatic contrasts, of dark, volcanic Maria and bright, ancient highlands, a world whose face has been shaped and reshaped by a long and complex history of both internal geological activity and external cosmic bombardment. The far side is a more ancient, more uniform, and in many ways a more honest world, a world that has been largely spared from the resurfacing effects of volcanism, a world that has preserved, with a stark and beautiful clarity, the deep and violent scars of its own primordial past. This fundamental dichotomy is not just skin deep. It is a reflection of a deep and enduring asymmetry in the moon's very structure, in the thickness of its crust, in the distribution of its internal heat, and in the fossilized remnants of its ancient magnetic field. And it is a story that has been painstakingly and beautifully pieced together by a long and heroic series of scientific missions that have taken us from our first, blurry and ghost-like glimpses of the hidden side to the detailed, high-resolution, and multifaceted understanding that we have today. The once hidden, far side of the moon is no longer a blank page in our cosmic atlas. It is a rich and complex and beautiful new chapter, a chapter that is not just about the moon, but about the deep, and often violent, history of our entire solar system, and about our own small and precious place within it. The journey to the moon has not just been a journey to another world, it has also, and always, been a journey home. A journey that has given us a new and more profound appreciation for the beauty, the fragility, and the sheer cosmic good fortune of our own, blue and white, and very much alive, planet Earth.